sir.
What about lecture today, madam?
Sorry, sir.
Hello.
Yes.
What about the lecture today? When it will be started?
Sorry, sir, your voice is breaking. We could not hear you properly.
Okay. I was checking from Bhopal, Madhya Pradesh. Just I would like to know when it will be started.
The session will be starting at 6 sharply.
Okay.
So it's now 6:02. We are about to start the session because our speakers have already joined. So now we are
Okay.
going to proceed with
Very
this.
good. Thank you very much. Thank you very much. Thank you very much.
Yes.
Okay.
Speaker has not joined, I think, ma'am.
Yeah,
He's
yet to
he's
join.
yet to
Yeah,
join.
actually there is some network connectivity issue from his end. So he's
Yeah.
trying to get it resolved as early as possible.
Mhm.
Meanwhile, we can do the announcement for the participants that the attendance sheet will be sharing in the chat box. Please do respond in each of the session. You have to mark your attendance. Please take a note that you have to mark your attendance for each of the session. And your attendance will be recorded and it is uploaded in the AICT portal. Right? Am I clear? So meanwhile, since we have 2 minutes time, meanwhile, any doubt, any problem from the participants side, that we can take it now. I hope I'm clear. And we'll be sharing the
Yes,
link
ma'am.
in the chat box. We'll be sharing the link in the chat box. Please be attentive in the session because you have to appear it in the test also, which will going to be held in the last day, last session before valedictory. So please be present throughout the session. You can take short notes also because you have to qualify the test. And whatever questions will be asked based on the presentation, based on the session presentation. No feedback link is required because feedback you have to submit it in the AICT portal. And also we'll be requesting you during the valedictory to unmute yourself and you can share your views or feedback in that valedictory session. That's all. So there will be no feedback link. All will be shared. The attendance link will be shared in the chat box. Okay, I'm done. So the speaker has joined.
Hello. Respected coordinator, Parma madam.
Yes, sir. Yes, sir. Tell me,
Hello.
sir. Yes, sir. Yes, sir.
Just type. Yes. Can we ask some questions? I have given you two questions previously yesterday. So
Sir,
when that will be clarified?
sir, sorry to interrupt you, but since our speaker has already joined, I would request you to take up your question later on in question answer session, sir. So please be there and we will discuss it later on. Over to you, Christy. Please go ahead.
Thank you, ma'am. Hello, sir. A very good evening.
Yeah, good evening.
If you say so, we can start.
Yes, sure. We can start.
All right. So, hello everyone. A very good evening. A very warm welcome to our esteemed participants and our esteemed speaker to have joined us on the third day of the Atal AICTE sponsored 6-day faculty development program on seismic vulnerability assessment, organized by the Department of Civil Engineering, Royal School of Engineering and Technology, the Assam Royal Global University. We are delighted here to continue with this academic journey with a very highly accomplished speaker who brings with himself immense expertise and experience. For both the sessions today, we have Dr. Kaustav Dasgupta. So just give me a minute to introduce you to our participants. Kaustav Dasgupta is currently an associate professor in the Department of Civil Engineering at Indian Institute of Technology, Guwahati. After finishing his undergraduate studies from Bengal Engineering College, Shibpur, now known as IIEST Shibpur, he worked for 3 years in industry, first in Development Consultants Limited, Kolkata, now DCPL, and then in Reliance Industries Limited, Jamnagar, Gujarat. At Jamnagar, he was involved in the design and construction of the world's largest grassroots refinery cum petrochemical plant. Then he joined IIT Kanpur to obtain his MTech and PhD degrees in civil engineering with specialization in structural earthquake engineering. Both his master's and doctoral research works were on improvement of seismic behavior of reinforced concrete shear walls. Since the last 10 years, he is working as a faculty member at IIT Guwahati. The research of the area of his research interests are seismic behavior of reinforced concrete structures, seismic soil structure interaction, and seismic vulnerability assessment of structures. He is also a member of the State Technical Agency for the Review of Bridges in Arunachal Pradesh under the Vibrant Village Program of the Government of India. I now request Dr. Dasgupta to take over the session.
Thank you, madam, for the warm introduction, and good evening to all of you. Let me first apologize for the small delay in joining. There was some network issue here, so I could not connect. Okay, so fine. So let me share the screen. Is my screen visible?
Yes, sir. It is visible.
Yes, sir.
Fine. So good evening again to all of you. So the first topic of today's presentation is numerical modeling of seismic soil structure interaction and overview. Okay. So this is the brief overview of my presentation. First, I will introduce what is the impact of soil on structural behavior and how soil structure interaction differs from our conventional thought of influence of soil on structural behavior. Okay, so then what exactly is soil structure interaction? We'll just have a brief overview. I will dwell upon the salient issues which are of concern and then move into the modeling part. So in the modeling part, we'll primarily focus on the numerical modeling, as is the title of the presentation. And we will discuss both the simplified methodology as well as how the detailed soil model is considered for more realistic analysis. And then finally close with a few notes. So for an introduction, let me first give the most popular example of the effect of soil on structural behavior as illustrated by the Leaning Tower of Pisa. So what happened was, since over a few tens of decades, okay, once the tower was constructed, slowly it started leaning. Okay, so when it started leaning, people were a bit concerned, and also they tried different ways of trying to restore it. Right. So when they tried to restore it in different ways, like making it stable by means of ropes, making it trying to buttress or prop at different locations, different heights. But all the time, even if it was restored for some time, for a certain period, again it started leaning. Okay, so people left it as it was, and then after a certain time, the rate of leaning came to a very small value, the rate reduced and reduced to a very small value, and probably in some way it got stable. Okay, so how this stability of the structure was achieved, how the underlying soil was affecting the entire behavior, entire tilting, was a topic of immense research over decades. Okay, so if we see the underlying layers below the leaning tower, it was very near the coast when it was constructed. Okay, in some point of time, the sea line also slightly moved away. Okay, and then primarily just below the ground surface, we have the sandy and clayish mud. Then it is underlain by clay soil of different stiffness, and then finally we have the stiff soil and rocks. So with this composition of the underlying soil, what happened was, when the initial leaning started, some kind of differential stresses were introduced there. So as you can see, when a foundation or any kind of element tries to bend like this part is trying to compress the soil more, right? So that creates more bearing stress or bearing action from the underlying soil. So the soil in this region is subjected to slightly more stresses, whereas here there is some kind of relief because it is kind of getting uplifted, right? So with this composition of the underlying soils, this probably made the things more easier or more facilitating for further leaning, right? And what happens is, when we have high stresses, the microstructure of these soils also undergo changes. Okay, uh, if you go into the depths of soil mechanics and the constitutive behavior, you will see that soil can pass through different phases depending on the strain level and stress level. So all those complicated the entire action, right? So people started different ways of finding out how best we can try to understand the behavior of this leaning tower. So whenever we talk about the underlying soil, the most simplest way is to consider some kind of spring. When we say spring, your spring can be like the conventional translational spring. Like if you give some displacement between two ends of the spring, either it can get elongated or it can get compressed, right? So depending on the amount of elongation and compression, the corresponding spring resistance will develop. That's what we learn in our +2 level physics also, as well as undergraduate level mechanics. Okay, apart from the translational action, where you have relative displacement between the two spring ends giving rise to the spring resistance, you also can have rotational springs. Okay, how does the spring resist rotational action? So the spring is designed in such a way that any kind of relative rotation between the two ends of this rotational spring will generate some resisting moment. Just like in translational spring, the relative displacement gave rise to some force in the form of spring resistance. Here, it will generate some kind of moment due to the differential rotation. So people use these rotational springs, people use these translational springs in different combinations in order to simulate the behavior of the underlying soil layer. So people tried in different ways. They have the foundation of the tower, and below that, the entire soil layers, all the three layers, they were attempted to be modeled using these kind of springs. So that's what I was mentioning. You have the spring coefficient for translational spring relating the force and the relative displacement. You have the spring coefficient for rotational springs relating the relative rotation and the generating moment. Okay. So under linear elastic behavior, whatever is the amount of rotation, proportional to that, moment will be generated. And similarly for your displacement and force. However, once we see the behavior of soil, right, uh, the behavior is not really linear elastic. Even when you have slightly larger strain level in soil, the linear elastic behavior does not hold good. Okay, it gives rise to nonlinear behavior. So in nonlinear behavior, what happens? Your spring coefficient, what we consider for translational spring, what we call consider for rotational spring, does not remain constant, right? For linear elastic behavior, these coefficients remain constant. However large the rotation may be, however large the displacement may be, they always remain constant. For nonlinear springs, these spring coefficients depend on the level of displacement or level of rotation. So beyond a certain level of displacement, the spring coefficient will keep on changing. Similarly for the rotational one. So when you have those clay type of soil, muddy type of soil, those soils go into this nonlinear behavior at slightly large level of displacement. Okay, so you keep on increasing the displacement or so, it will go into nonlinear behavior. So that's how nonlinear springs are more appropriate for modeling the soil behavior, right? So that was in one way. You can have the lump springs, or below the foundation, you can have a number of translational springs, as you can see here. So what is the difference? In the previous one, you had only one spring in the vertical direction, trying to model the settlement of the soil layers below the leaning tower. If there is some tendency of sliding, this single spring is supposed to take care. And then if you have any rotational action, this single rotational spring is supposed to take care. So you have only three springs in one plane to simulate the soil behavior. Rather than that, because the foundation is quite large, because if you see the diameter of the tower, it's in tens of meters. It's not like 3-4 meters or 5 meters. So beyond that dimension, this single spring lumped modeling does not give you really realistic behavior. So people tried with number of springs in this distributed way, considering the underlying foundation like a plate action over which the tower is standing, right? And then they tried to simulate, right? So that is one slightly advanced way of modeling the soil. Instead of a single one, we use distributed springs. Okay, so that way also people try to model. So when you have such distributed spring and there is again this kind of tilting, one part tries to get uplifted, one part tries to get compressed. So this is how the spring behavior will change. One of the spring will be under compression, so it will be compressive resistance. This spring will be under tension because trying to elongate. Okay, so likewise. So those were the spring modeling. Then people thought that instead of this spring action, why can't we model some part of the underlying soil like this kind of domain, right? So in domain, what we do, we generally adopt the numerical method known as finite element method, okay, which is very, very popular over last century. Okay, so there are different ways of considering what will be the size of the domain, means how will you decide these elements in the entire domain and so on. So people have done a lot of studies. So people also attempted this kind of domain modeling in order to simulate the underlying soil behavior, because people wanted to understand why is it leaning. In spite of being trying to restore, it's still going on leaning and leaning. Okay, what can be the reason? So you consider the ground level as one extent, and then towards the sides, it's like infinite domain. So you have to limit the domain up to certain extent. Towards the depth also, below the soil, there will be rocky layer as we had seen. So you have to consider some limit of the domain. So people tried in that way also. So this is the third way of modeling the soil for this leaning tower of Pisa. Okay. So all these methods were attempted, but uh, these were giving some kind of understanding, but not full understanding. So till date, probably it has not been established why the Leaning Tower of Pisa really started leaning and continued for a number of years. Okay, so these were some effects of the modeling of soil on the structural behavior. These are how we can do. Okay, so let us look at a small example. Okay, that was a practical example. Let us now look at some numbers. Okay, so when we do structural analysis for any kind of normal building or conventional structure, small structure, we never consider the effect of underlying soil, right? So that's not the part of the conventional design process, okay, or the analysis part. So let us see, if we take a portal frame of certain height, say 5 meter, certain bay width 5 meter, and these are the beam column dimensions 230 mm by 300 mm. So what we are going to do, we are going to have 4 types of modeling method, okay, under a lateral load. So how does the portal frame look like? This is how the portal frame look like. Portal frame is the simplest frame in a plane consisting of 1 beam and 2 columns, right? So here we apply a lateral load of certain value, and we want to see how are the columns and the beam responding through the bending moments, right? Because under any applied load, the members will generate shear force and bending moment. We all are aware. So we are considering 3 types of soil. One, which is very soft, okay, similar to the upper layers of Leaning Tower of Pisa. Then we have medium stiff, and then very stiff. Very stiff means we are now going close towards the rocky behavior, where the deformations and those things are very, very less. Okay, so we want to see that how the bending moments are generated on this portal frame. So this is how the frame looks like. And then the first case, what we are considering is that all the degrees of freedom at the base are restrained. Okay, so one is the fixed base. That is the conventional method of analyzing any kind of building frame. Okay, when we do not want to consider any effect of soil, we simply consider all the translational and rotational degrees of freedom to be fixed, right? So no rotation, rotations are 0. No translation, translation is 0. In reality, does your soil really conform to that condition? No, because depending on the stiffness of soil, there can be settlement. So settlement means the translational degree of freedom has to be allowed. The your frame can tilt, just like Leaning Tower. So there can be some rotation. So your rotational degree of freedom also has to be allowed. So in reality, your degrees of freedom being completely restrained is not going to happen at all. Okay. But then why do people consider that in conventional analysis? Because even if you consider this fixed base, okay, so the estimated moments and shear forces what we use for design, they are expected to be on higher side. So your design is going to be conservative and safe, right? So people are really not bothered about the effect of soil. So that was the first case. Second case is we assigned the translational rotational springs, just like we saw for the Leaning Tower of Pisa. That is case 2. And case 3, we are going to have the soil model as continuum. So the domain method, we call it a continuum method. Like the soil is like a continuous medium. We are discretizing in a certain way and then considering that extent of the soil. So we have 100 meters on horizontal side, that is the size of the domain, and to a depth of 30 meters, right? And the case 4, when you have the soil modulus continuum with the same properties, but with flexible boundaries. Okay, so these are the 4 cases. Let us see the results. Just on the portal frame, we want to see the effect of soil through the different kinds of modeling. So this is how the case 1 will look like. You have fixed bases, right? No degrees of freedom has been released. Okay, these are your translational and rotational springs, as we had seen, the vertical horizontal ones and the rotational ones. That is case 2. Case 3 is your this domain. Okay, as you can see, you have your soil domain 100 meters on either side, it is extending, and 30 meters deep, and then the end nodes have been kept as fixed, right? So that is case 3. On that your portal frame is sitting, right? So, and similarly, when you have case 4, you have these boundary ends. These are with springs, right? So these are not fixed. That was case 4. So if you see the result, what happens when you have completely fixed base, that is no effect of soil, you can see how much is the magnitude of bending moment. It is around 714 kilonewton meter at the column base. And at the column top or the beam end, it's around 530 meters, right? So this is the conventional method, no effect of soil. And this is supposed to be giving you the overestimation of forces and moments. So this is case one. Let us look at case two. So in case two, you have on very soft soil. So one is with continuum soil model with boundaries. So this one, when you have the soil domain, that is 2A. And then second one is your 2B. That is when you have equivalent soil springs, right? So how did we model soil? In one case, it was with springs. The other case, it was with soil, this domain, right? So this one is for the very soft soil. So what happens here? When you have the soil model as this domain, this is coming out to be more realistic because soil is in fact occupying a certain volume. So when you are modeling this extent of this soil, so this is going to be closer to your realistic soil model. Okay. When you are lumping the entire soil domain through springs, that is also an approximation, right? So when you are using this domain model, that is 2A, your bending moment has reduced from that 714 in the previous case, where you did not have any soil, to 284, right? So there is a significant reduction in the bending moment. Okay. What happens at the top? The column moment has reduced, but at the junction, okay, what has happened? Earlier the moment was 530. Now it has become 960, almost twofold increase. It has become twice. So what has happened? The bending moment at the bottom of the column has got released, okay, and then more moment has been accumulated at the junction, right? So this was with the soil domain, most close to the realistic one. And when you have the springs, what happened? The bending moments at the bottom of the column definitely were reduced as compared to your fixed one. From 714 with the spring, it has reduced to 596, around 600. But it has not reduced to the extent when you model using the soil domain, right? So with the spring, definitely your soil behavior is affecting, but your domain model is coming out to be the best one because that is really giving the relieving effect of the soil at the column bottom, right? And at the junction, what happens? Since the reduction at the column bottom is not that much, the beam column junction, there the moment has increased, but not as much as the increase in case of the domain model, right? So this shows how your different cases of soil modeling, different ways of soil modeling really affect. So this was on very soft soil, right? If you look at the medium stiff soil, this one, so same way, this one is for the domain model and this one is for the lump spring model. So as you can see, the bending moment here, since the soil is medium stiff, so the soil stiffness has increased, so the domain stiffness has also increased. Once it is increasing, that means the column bottom moment is also going to increase. Still, it is less than what was there when you did not have any soil, fully stiff condition, maximum stiffness. So as compared to that, this has reduced. But then as compared to very soft soil, since it is medium soil, the bending moment is more. Okay. Same is the case for your soil model using springs. As compared to domain, the stiffness is more. So the spring model is giving you higher bending moment. Once it gives higher bending moment at the bottom, at the beam column junction, less bending moment is there. Because whenever you apply force on any structure, any assembly of members, the forces and moments, they get redistributed. Okay, whichever part is more stiff, force and the moment will try to accumulate there. They become more stressed. The part which is more flexible will try to relieve the forces and moments to the stiffer parts, right? That is the natural behavior. This is the principle based on which all your structural analysis results are obtained. This is the simpler way. Okay, so given any complex structure, if you can identify which are the stiff parts, which are the flexible parts, less stiff parts, you can easily figure out where you will expect more design moment, design force, where you will expect less design moment and less force. Exactly same thing is reflected here, right? And then when you have very stiff soil, now it is going closer to that condition of rock. In rock, what will happen? If you have the column embedded in rock, how do you carry out the construction of the foundation? You can provide shallow footing because you have very good bearing capacity. Rocks can offer uh, immense bearing capacity. So you need not go for deep foundation. Okay, what's the use? So in the rock, if you have to do some foundation, you go for open foundation, shallow footing. Okay, and that too you have to drill the rock, right? If the rock is very hard, then depending on that rock quality designation RQD, you have to do the blasting and then find out the area, then do that. Once you have a open foundation in the rock, it does not have the ability to rotate, does not have the ability to translate in any direction. So it is more like that, all degrees of freedom restrained, close to the fixed base. So for fixed base, if you recall, your value at the bottom of the column was 714 kilonewton meter as bending moment. And here for the very stiff soil, it is very close. It is less, but it is very close. So as you can see here, your domain model will still give you less moment as compared to the spring, right? So anyway, so this is how the modeling of soil is going to affect the structural behavior. Still, we have not come to the soil structure interaction. This is not soil structure interaction, right? You have to be very careful. You apply some static load, and depending on soil model, your bending moments and shear force get redistributed. You are happy with the small value here, large value there. That is not at all the soil structure interaction, right? So that's how we look at it. Okay. So whatever we discussed till now, it was influence of soil on structural behavior as exemplified by the leaning tower or the frame behavior. Okay. So no SSI till now. So then what is SSI? Okay. What is all the hue and cry about soil structure interaction? So if we want to see what is the soil structure interaction, we have to briefly first start with how the earthquake mechanism happens. So typically we have some release of energy in the crust of the earth, in the mantle of the earth somewhere, or in the crust of the earth, depending on the depth. And there is a fault rupture somewhere, energy gets released, and the energy gets propagated by means of waves. So when you have waves, they have to follow all the mechanics and physics as we studied for waves in our plus 2 level, class 11, class 12. Okay. So you have reflection, you have refraction, you have total internal reflection, and whatnot. Everything happens. So these are called seismic waves. If you read more into that, you have body waves, we have surface waves, and so on. So initially, the body waves propagate through the rock, then they reach the soil domain. This brown part is your soil domain. And then they reach the surface. During this entire propagation through the soil domain, the waves keep on changing their characteristics. The amplitude, the frequency, all get changed depending on the layers of soil, depending on their constitutive properties. So waves undergo changes. So when they undergo changes, the final wave, which is reaching the surface, here also some part gets traveled along the surface, which are called surface waves. Some part gets turned back inside the domain. They will again propagate and spread out. Okay, so a lot of wave phenomena carry on, keep on happening. So most of our damages and vibrations and shaking, what we observe, are caused by the surface waves. Sometimes we have body waves also. If your structure is located very close to the fault, okay, then you can have the body waves also coming quickly, and then they can cause huge shaking. Okay, so this is how the things happen. So you have rocks, then soil layer, then foundation. Once the foundations get shaken up, your vibration, the building also gets shaken up. So how does this happen? Your when your surrounding soil is shaking up the foundation, your foundation starts vibrating. Once the foundation starts vibrating, your beams columns start vibrating, and it propagates upward. Now, when your initial soil was vibrating, that time in the initial part, foundation was still. Superstructure upper part was also in a still condition. It was not vibrating. Now, since the superstructure has started vibrating, that vibration is going to affect the vibration of the foundation. So the vibration of this upper part is going to affect the vibration of the lower part. Now, this lower part is again surrounded by soil. So the vibration of this lower part is now going to affect the vibration of the surrounding soil, right? So initially, soil was the cause of the vibration, soil shaking. It shook up the foundation, foundation shook up the superstructure. Now, superstructure is now affecting the shaking of the foundation, foundation is now affecting the shaking of the soil. So there is a mutual interaction between the shaking of all the three components, your surrounding soil, your underlying foundation, as well as superstructure. So once you have this interaction happening, that is called soil structure interaction, right? So soil and the components of the structure, they are affecting each other through different properties. And then that is how the actual behavior gets mobilized through this interaction phenomenon, right? So what is the prerequisite? You must have shaking, dynamic phenomenon, right? Not a static load. Once you apply a static load and just see the stresses and so, it is not interaction, it is one way. So SSI has to be both way, two way, soil to structure, structure to soil, and so on. And that will happen over the entire duration of the shaking, right? Because the waves will keep on coming, and then after some time, so when we feel earthquake, what happens? Initially, the shaking is less, right? Small shaking. Then suddenly it increases. We really feel the shaking, okay? And then again it dissipates, right? So in the same way, over this entire duration, this both way interaction coupling has to take place. So that is your soil structure interaction. So it has to be dynamic, and both the components have to be talking to each other that way, okay? So that is the prerequisite of SSI. So this is how it's a very nice figure by Jonathan Stewart, one of the pioneer geotechnical earthquake engineers and academician. So this is how you get. And then when we study the soil response, what happens is, if you did not have this building, it will be called free field effect or free field vibration. Only soil is there, no foundation, no structure. When you have the foundation of the structure, then the SSI starts. So if you do not have structure, no SSI, only vibration of soil, free field effect. But once the structure is there, you will have the SSI, right? Fine. So what kind of foundation will show you SSI? If you have an open foundation, right? If you have very good soil or even rock, what will happen? The waves will come, just shake up the open foundation, shake up the above structure. So that will be done. So then there will be some back and forth motion. But the extent of the foundation is small. So interaction zone of the open foundation and the soil is very less. To have the real effect of SSI, you need deep foundation. And in deep foundation, piles and well foundation, they are the most common one. Well foundation we use for bridges, right? So this is how it happens. As I was mentioning, shaking up of soil causes deformation in piles. Vibration of piles will vibrate the superstructure. Superstructure vibration will affect the pile vibration, right? Pile are long elements embedded in the soil. And then the vibration of soil, surrounding soil, will be further influenced. Okay. So this is the repeated interaction which we call as soil structure interaction, right? Hope it is clear. So when you just model the soil as it is, apply static load, it is never an SSI. So if you say, see or hear somebody talking that as SSI, it is not at all correct, right? So please note that. So this is how your piles will be embedded in the soil domain, okay? And then when you look at the boundary, what happens is, when you have the waves coming and affecting the surrounding soil, the soil will vibrate the piles and the entire shaking will propagate upward, right? Now what happens, some of the waves also turn back, right? In all the directions, in all the directions, the waves will be turning back, right? Some of them will get reflected from the pile surface and turn back. Now when they turn back, what will happen? Your waves will again go and dissipate away into the largest soil extent, okay? they will not be going to affect. When for numerical modeling, we are considering that soil domain, right? Remember, for the Leaning Tower of Pisa, as one of the cases, we considered some extent of soil domain, 30-meter depth and 100 meters, some number. So how you model this boundary, it is very important, because if you give fixed boundary, what will happen? The waves which are getting reflected from the piles will again reach the boundary, and from there they will find fixed barrier wall kind of thing. Again, they will get reflected back into the domain. Then again, we will, some part will go again to the pile, some part will go to the other boundary. Again, from there they will get reflected. So this multiple reflections and so on will keep on happening, and all those waves will get trapped up inside this domain. The waves will not be able to go away. In reality, the waves dissipate away, right? But then if you model these boundaries as fixed boundaries which can reflect the waves, your waves cannot be traveling away. You cannot get that effect. So your soil domain will keep on vibrating, your piles will keep on vibrating. That is not how the realistic vibrations will take place, right? So, how should we do? So, we consider the boundaries as absorbing boundaries. Why do we call it absorbing boundaries? Because the waves will get absorbed, right? So that they won't get trapped and keep on reflecting. So, absorbing boundaries have to be provided at these extents, okay, at these limits, so that the reflected waves get absorbed, and similar way they will get dissipated in the realistic sense, right? So that is one way of modeling these boundaries. Okay. So if you model these as fixed boundaries, as we had done for one case for the Leaning Tower of Pisa, it will not give you the realistic soil structure interaction, because the waves will get trapped and keep on reflecting. So when you do the SSI, again, the conventional modeling or the restrained footing will not give you your SSI, because when you restrain the degrees of freedom, all your effects of soil are gone. So this is not the way, right? Then what should we do? When we do the simplified modeling, we consider as multi-degree of freedom system, right? So for multi-degree of freedom system, we convert it into an equivalent single degree of freedom system, right? Like an inverted pendulum. This is the very conventional way in structural dynamics we do that. Okay, when you do the dynamic analysis, you sometimes convert it for simplified method to an equivalent single degree of freedom system. So why do we call this multi-degree of freedom system? Because at different flow levels, as you can see, the masses are lumped. Most of the masses can be lumped at flow levels, and then at each level you can consider some displacement, right? So you can have different degrees of displacement at different flow levels. So multiple degrees of freedom, multiple translations are required to describe the dynamic behavior. Instead of that, if you have a single degree of freedom, only one translation, one displacement to describe the behavior, that is simplified. Okay. So why is this equivalence really required, or people use that? Because for a single degree of freedom system, just like you know the behavior of a simple pendulum from your 11th and 12th physics background, you can easily find the natural period of vibration or natural frequency, and that can be related to the earthquake behavior. Okay, whenever you talk about seismic behavior, your natural frequency, natural period, they are very, very important. Okay, whenever we do any seismic analysis, dynamic analysis, first thing we check in your numerical model, how much is the natural period coming, how much is the natural frequency coming. Okay, that will give you the idea whether really your modeling is correct or not, because you have some physical experience that okay, this can be the range of natural period, right? So when we look at the seismic behavior, now let us come to the uh, Indian scenario. In Indian scenario, we use the uh, document published by the Bureau of Indian Standard, BIS, that is the Indian Standard 1893 Part 1, okay, for specifically for buildings, and that was last revised in 2016. So this figure is known as design acceleration response spectrum. Okay, I'm not going into the details of the figure. Okay, what it does, It considers the natural period on this x-axis. Whatever you have estimated as the natural period, it will consider that and then find out that what is the level of acceleration. Okay. When you have earthquake shaking, basically you have the dynamic behavior, the shaking of the soil. So it changes with time. Initially small shaking, then large shaking, then again small shaking, coming to again still condition. So that changes with time. But when you do the structural design, considering this dynamic behavior sometimes becomes very tedious, especially if you have a big building, okay, very complicated model. So churning out the results, finding out the design values is very, very tedious and may not be accurate also. So what is it is done? We don't consider the dynamic effect of the ground shaking. Rather than that, we consider on your model equivalent static load. So we convert in some way the equivalent static load. So this response spectrum is one step in this conversion of this dynamic effect into the equivalent static load to be used for design, right? Whatever this figure is proposed in IS 1893, this is going to be used for design, not for anything else. Okay, if you really look at response spectrum, it is never such a smooth curve, such a nice looking curve, never. Okay, there are a lot of irregularities, ups and downs. So to simplify the things, to make it easier for practical designers, this document has published such a nice figure. Okay, so this is used to estimate the equivalent lateral forces, which is going to give you the earthquake, uh, the design seismic forces, right? Design shear force, design bending moment in combination with other loads. Okay, so when you have a stiff system, suppose when you have the conventional one with all the degrees of freedom restraint, what we have here. So it's very stiff. There is no soil. Okay. So for a stiff system, what will happen when you have large K? K is the stiffness. You have your natural period coming down because denominator is large. So you have low natural period, and then the acceleration is more, right? And then you have the estimate as conservative estimate. And when you have presence of soil, what you have, the K is now less because either you are considering spring or you're considering the soil domain. So K is less, so natural period is more. So the system is flexible as compared to the fixed pace. So increase in natural period. So on the x-axis you are moving, and that will give you less uh, acceleration, right? Because you are now looking at this part, you can see the curve is coming down. So in this region, the acceleration is less. So your design forces are less. You are going to have less bending moment in the column, less bending moment in the members close to the soil, as we had seen for our frame, right? So the response is less. So when you are considering the conventional structure with the base fixed, you are considering higher design forces due to the large acceleration. So which is give you a safe design. May not be economical, but safe design, right? On the other hand, if you consider soil, your response is less, so shear force bending moment is less, right? So everything comes down. Right? Then the Indian code also prescribes three curves, as you can see, for the different types of soil. So as you can see, you will have different effects for the same natural period and so on. Right? So if you ignore the effect of soil being dynamic behavior, you are going to have safe design. That is what we expect from that response spectrum. And if you consider, you expect less response. Does it happen always? That is the question. Like whenever earthquake will come, your response spectrum is going to give like that. So as we have seen. So does this happen? Does the ignorance or considering no soil, fixing all the degrees of freedom, does it always give you safe design? Right. So that is the question. Let us look at uh, a series of response spectra for different earthquakes. So as I had told you, when you consider a particular earthquake and see the response spectrum, it looks like this. Like if you look at one earthquake in this form, okay, this 1995 Kobe earthquake, which caused widespread damage in Japan, very famous earthquake in earthquake engineering research. People have done a lot of work using the ground motions. People have learned a lot. So there you can see there are ups and downs, right? All the earthquakes, the individual earthquake has the response spectrum like this. But when you look at the design one, similar to this one, the smooth curve, what IS 1893 prescribes, okay? So this is the design one. Now, if you consider a flexible system, suppose now you're considering soil, so your natural period is more, as we had seen. So you are now in this part, 1.5 second, 2 second, like that. If you consider this Mexico City earthquake, you see this spectrum, okay? This reaches the peak acceleration very high. At which natural period? The period is slightly more than 2 seconds, 2.05 or something. So when you are considering soil, you are on the higher natural period range. At the same time, for this earthquake, it gave you much larger acceleration. Consequently, the force will be much larger if you did not consider the soil, right? So if you had considered soil, if you did not consider soil, fixed space, your natural period would have been here. Your Mexico City earthquake would have given some maybe acceleration in this level.
Sir,
Maybe.
sir,
Yes.
sorry to interrupt you. We could not see your slides.
From where can you see now? Can you see now?
Sir,
Oh,
we
sir,
can able to see, sir.
Ma'am, it's
It's visible.
it's visible.
okay. So in my system, I think so some problem might be.
Okay, okay,
Sir,
okay.
okay, you please continue. Very sorry for that.
No problem, no problem. Okay. Okay. So what I was saying is, if you had considered, say, the design spectrum and did not have considered the soil, so you would have considered that is an amplification, say 2.5. And now, if you consider soil with the large natural period, your acceleration is going to be more than twice, right? Close to 6. So for this earthquake, if you are not considering soil, if you are not going to have the natural period in this range, your structure is definitely going to be grossly unsafe. And that exactly happened in case of the Mexico City earthquake. So this happened in 1985, okay? And then a particular class of buildings, a certain height of buildings, they collapsed. Neither the very low rise ones nor the very high rise ones. So over a certain range of natural period, the natural periods of the buildings which were lying in this range, right? So they were the ones which got affected, okay? Because for them the magnitude was very high. So those buildings were probably designed for this level, okay? And then the natural period of those buildings were in this range. So they experienced a force more than twice of what they had been designed for. So a certain range of buildings got collapsed. So this was an eye opener that in certain cases, if you do not consider the soil, if you do not consider that soil structure interaction, your design is going to be unsafe. You are going to have very unsafe buildings. Similarly, for this one also, when you have your this Kobe earthquake at Takatori station, EW means east-west. Whenever we record earthquake ground motion, there can be three components: two horizontal components. Generally, the accelerometers, they consider the north-south direction component as one record, east-west component, the perpendicular ones, as one record, and third is the vertical. So whenever you see EW, that means east-west. So if you look at the Kobe earthquake at Takatori station, here also the peak occurred, say, around 1.25 second. So with the soil. So if somebody has not considered soil, considered as fixed base, that building would have been designed for this level of acceleration. And now with the soil, because when earthquake comes, the building doesn't know that you have considered my bottom as fixed or with soil. Okay, the building will behave as it is. It is on the soil, soil will get shaken up, and the foundation will shake up the building. So in reality, for certain cases, if you do not consider the soil, you are going to have unsafe design. So that brings the necessity of the soil structure interaction. So these are the points where your unsafe design can result due to ignorance of soil. If you ignore soil, you are going to have the design at this level, and the actual behavior will give you higher force, right? So that's why under this condition, this is how you calculate the uh, design horizontal acceleration when you estimate the design loads as per IS 1893 part 1. So you look at base shear. So this depends on the acceleration. So your entire this SA by G is based on this response spectrum, okay, for design. We do not consider these things, but in reality, these will be happening, and probably your building will be going to collapse. Okay, so that's why beyond this range, all these points, wherever you have large acceleration, they are going to be the critical cases, right? So where can this happen? If you have the underlying soil deposit going to very deep, like the Mexico City, this city lies in a big valley. It has surrounding mountains at very long distance. It's a huge valley like a basin, and it has very deep soft soil layer over a large extent. So what happened was when the earthquake happened, in that part, the your the soil deposit caused large elongation of the natural period, and only for those buildings, those height of buildings where the amplification was maximum, they were uh, undergoing collapse, right, during the earthquake, right? So it happened during 1995 Kobe earthquake also. Okay, so sometimes you have the soil deposit happening. There is also a particular uh, terminology when we in earthquake engineering, this is the directivity of rupture. Like when a fault gets ruptured during the release of energy, in which direction it is rupturing. Okay, so if a fault is oriented along from south to east to northwest, is it rupturing from northwest to southeast or from southeast to northwest? So along the fault you may have different buildings, so depending on the direction your amplification can change, right? So there are different effects, long period pulse filling effect for this near fault motion. So all these can lead to these collapses. Okay, these can amplify that soil structure interaction. Okay, this is one spectacular collapse, and in any earthquake engineering failure presentation or discussion, this photograph comes up. This was an expressway in the city of Kobe, and in 1995, that Kobe earthquake, also known as Great Hanshin earthquake, that caused the collapse of this expressway over a few kilometer stretch. As you can see, the superstructure, what we have for a bridge, that is the deck, girder, your railing, footpath, all the accessories. You can see the girders, the transverse girders, the longitudinal girders, okay, and these are your piers. So between the piers, you can hardly see any damage. This entire thing has toppled, just tilted. All the damages have been concentrated in the piers, and that too in the pier bottom. So what happened was there was a certain level of design considered. I'm not sure whether soil was considered or not. What happened was the underlying soil amplified the response, and that caused the damages in the underlying footing, foundation part, and your pier. Okay, so this part got the most damaged. So although your superstructure is undamaged, but this is almost unusable. How can you restore it back? Okay, so this was a great learning lesson for the Japanese. Okay, we all know that Japan is a pioneer in understanding the earthquake engineering and behavior, but for them also, they didn't expect that such and a long extent of expressway built with so much money can collapse like this. Okay, so this was a glaring example of how soil structure interaction SSI can affect the structural behavior, right? Fine. So that much for the background. Why SSI is required? Let us look at the salient issues quickly. So the major input is the ground shaking. When you look at ground shaking during earthquake, we express in terms of acceleration varying with time, velocity varying with time, displacement varying with time. And how are these plots going to look like? Your plots will be like initially when you feel small shaking, it will be less. When you have large shaking, it will be more, and then it will be subsiding. Then soil properties, these are very important, okay? Whether you are going for simplified model or detailed model, how you are using constitutive properties. Constitutive properties of soil are they are very, very important. Why? Because as you know, depending on the type of soil, you have different behavior. You can have dilation, you can have phase change. If you talk to some geotechnical person, one can explain you phase change. So all those affect the behavior. And especially during earthquake shaking, what is happening? You have over a small amount of time large strain in the soil, because when the ground is shaking, there is large shear strain, right? When the waves propagate from rock to the upper layer, the soil layers try to shear against each other, right? Horizontal movement. So shear strain momentarily increases, very large value. So when the shear strain increases, the damping, your damping ratio, the shear modulus, all get affected. You have standard curves for change of the shear modulus or damping ratio, right? So those are very, very important. How you model the soil and what are the constitutive properties, right? Whether you are considering drained condition, whether you're considering undrained condition, because over a momentary time, since the strain increases, the stress goes up, the pore water pressure can go up to very high extent. And depending on the type of soil, if it is sandy or sandy silt, or for certain soil, the soil can liquefy. So you can have liquefaction during the soil structure interaction. So all these are very important. And then you of course have the substructure foundation properties. Those also will come, and superstructure property will come, because when we talk about SSI, from superstructure to the soil, all are affecting each other, talking to each other, right? Then we talk about near field effect, okay? When you have ground shaking very close to the fault, then you can have the interaction close to the soil foundation interface. You can have far field effect when the fault rupture is at very far away location, and then when the waves come and come at the site, you can have different kind of far field effect, okay? So different connotations, different effects are there, okay? Just to familiarize with you the different uh, terminologies and effects, right? Let us now come to the modeling, okay, the numerical modeling part. So I won't go into the very deep detail, but then we will give you the good overview, right? So what we have, the first one is your lump spring, what we have already discussed. So in the lump spring, what happens? You have your 3 degrees of freedom for translation, and you have the translational springs I had mentioned in the Leaning Tower of Pisa. For all the 3 directions, you also have 3 possible rotations: about x-axis, about y-axis, about z-axis, right? So about those axes, since you can have rotation, you can also model the rotational springs, which will give you the moments, okay? So you can have like rotation about the vertical axis, that is like a torsion. About the column axis, the entire foundation of the pile cap is rotating in the horizontal plane. Okay, so that is your torsional stiffness, right? Torsional moment. Then you can have rocking. Your entire foundation can rock back and forth like this. So about x-axis, you can have rocking. About z-axis, you can have rocking, right? So this is how your soil, the entire soil underlying, that is being modeled using these springs only. So these 6 springs are going to give you the underlying soil behavior. So this is very, very simplified, because we know that over a certain extent of soil, your behavior will change from one zone to the other. So approximating the entire zone by means of these springs is grossly approximating, right? So this is how, this is the most simplified way. Then you have distributed spring, again in the Leaning Tower of Pisa I had mentioned. So how do we do that? You have the foundation, and then you consider a number of these translational springs and attach them to the rigid layer, right? So all these springs are supposed to take care. Now, what about the rotational behavior? When this foundation tries to rotate, it will get tilted, right? The foundation will get tilted. So some springs will be under tension for the uplifting part, some springs will be under compression to the bearing part. right? So there will be the effect of the rotation coming on this translation spring. So a single spring will not be able to capture this rotational effect. But when you have multiple springs, you can capture to some extent, right? So this is the distributed spring model. So this is one step better approximation of the underlying soil behavior, though not fully. Okay. So here when you have distributed spring, typically used below raft foundation, right, or mat foundation. Okay. Whether you have raft with piles or without piles, below the raft, we consider distributed springs. So nowadays we have different programs, commercial program softwares, trying to model the slab as a plate element, and then you can have these springs. How do you get the spring constant? By considering the modulus of subgrade reaction. Depending on the type of soil, certain values of K are specified, okay, and that's how you do. So for design level, quick approximation, maybe on the conservative side, this spring model as distributed one is quite good, right? That's why people use when people use in design. That means it must not result in unsafe or unconservative values, right? So this is the second way. Third one is if you do not have only the translational springs, linear elastic springs, you can have elastoplastic springs. So you can have one elastic spring and another plastic element. So there is a combination. How does it work? So whenever there is some settlement or deformation or some tilting like this, the rod will tilt like this. So up to a certain level of displacement, the linear elastic behavior will be captured by this part. Once it crosses that yield limit, then the plastic element will take care of the inelastic behavior, right? So in the overall displacement, if you have large displacement, up to the linear elastic part, this will be active, and beyond that, the plastic element will active. So this is one level of approximation to take care of the nonlinear behavior of soil. As I was mentioning, beyond a certain strain, most of the soils show nonlinear behavior. They don't show the linear elastic. That you reverse the strain in the same path, the stress values will also be reflected. It's not happening like that, right? So certain yield criteria need to be specified for transition, where the yielding will happen, and so on. Then the most common one, which is used not for design, okay? So when you do soil structure interaction, rarely it is used for design, okay? Most of the time it is used for evaluation. So you design the structure, you design the foundation, then you want to see under actual earthquake how your foundation will behave, how your surrounding soil will behave. That time the SSI comes very handy, okay? Most of the cases, that time the SSI is used. So the most common one is the nonlinear Winkler springs. So what happens here? You consider the nonlinear Winkler springs specifically on deep foundation, like piles. So piles are considered like beam column elements. Okay, and then you have certain nonlinear springs and dampers, right? So let us look at the figure here. So when you have the superstructure, you have the pile going deep inside the soil. So when you look at the soil behavior, one part is the stiffness. Like when the pile bends, how much active pressure will be applied by the soil, how much passive pressure will be applied by the soil, right? When a pile is bending, some part will be under passive zone, some part will be under active effect. So that will be taken care by the spring. But then when you have ground motion, because the waves are coming and vibrating the surrounding soil for the pile, how your soil is going to damp the vibration, right? Because whenever you talk about dynamics of any system, damping is a very, very important term, right? Very, very important property. So damping has to be estimated very, very carefully and quite accurately, as much with as much accuracy as possible, right? So in order to specify the damping, we use certain kind of elements known as the dampers, right? So again, there have been studies how the damping has been modeled, and they're going to be modeled. So you have springs to take care of stiffness, active passive effect. You have dampers. So you need to specify certain curves to take care of this stiffness and things. So you have nonlinear py springs. Why do we call py? P is the soil resistance, y is the displacement. So you look at certain py curves to take care of the soil resistance. Okay, then you need to have curves to take care of skin friction. Depending on the soil, you can have skin friction mobilized, especially for floating piles, right? So all the things are taken care. You need to give some property for end bearing. That's what we have, these ones, py and tz curves. This is the end bearing curve, this is the lateral resistance curve, and so on, right? So this is how you have the BNWF model, right? So again, it takes care of near field effect, it takes care of far field effect. So if you do not have the structure, you have the free field soil effect. Okay, based on the free field soil, you can find out that when the waves are propagating, how the ground motions are generated at different levels, which you need to give. So uh, when you consider the vibration, you will have large vibration in the vicinity of the pile, which will lead to more damping, which is taken care by the near field element. When the waves dissipate out, you have radiation damping, which is taken care by the far field element, right? So BNWF model is very, very realistic, tries to do. Okay. So now when you come to the detailed model, so these are all using certain kinds of springs. Okay. Among the spring model, BNWF is the most efficient one. Then when you come to the continuum approach, that when we model the soil domain, right? So what do we consider? It is semi-infinite, linear, elastic, homogeneous, right? So that is the simplest assumption. In reality, again, the soil is not going to be elastic. You don't have homogeneity, you can have different soil layers. Okay, so this is the most simplified assumption in the continuum approach, right? And then you build upon that the different variations. So what you have to consider the vertical extent of your soil domain, because this is the rock layer. So you have to model wherever you are modeling the soil. Suppose you are modeling the soil here below the building, you have to consider the depth appropriately. So you need to figure out how deep is going to be your soil layer in the numerical model, right? In your finite element model. So do you want to model it right up to the rock layer, or you don't want to model because this soil layer is very, very deep? The more you model the soil, the more difficult will be in your computation, because your program has to run in the finite element analysis. It has to churn out so much data. So it becomes very, very difficult. How much will be the extent in the horizontal direction? That also need to be established, the horizontal extent. And that you can obtain from the free vibration of the soil, right? So there are different methods. So this continuum method is the most realistic. Among the three different spring methods, BNWF is the closest to the reality. Now here you are looking at the most realistic one. So when you do the free vibration analysis, this is how you try to obtain the natural period of the soil depending on the shear wave velocity. Okay. And when you try to model the soil domain, what will be the size of this element, right? That also needs to be specified. If you are going for very small element, you can do that. But then the number of elements in your soil domain will be very high. So your computer will take more time. You need very high speed computer to run your model, okay, which will be quite difficult. Okay, so you need to figure out, because we all are engineers, right? We cannot be like theoretician. We keep on running computer programs for days and weeks, and then finally we land up in no useful result. No, it is not our purpose. We all should be look at the engineering point of view. In a certain amount of time, limited time, how efficiently we can run the system. So that brings us to the specification of maximum size of element. So these two persons, Leismer and Hulamer, they did pioneering work a few decades back, and they did a lot of work on this soil dynamics, how the soil domain can be decided. So depending on the wavelength of the seismic wave, the incoming wave, you can get a measure of the maximum size of element. Okay, so you cannot use very big elements while modeling this soil domain. That will not give you accurate results. So this is how you can relate with your short wavelength as well as the maximum frequency as well as the shear wave velocity. There is a book by Stephen Kramer, right? on geotechnical earthquake engineering. Very nice book, and gives you a lot of insight about this soil behavior during earthquake, this modeling part. So Stephen Kramer's book, if you are interested, please go through that. All these are very nicely documented, right? So this is one typical glimpse of what I wanted to show you. This is the detailed soil domain model for the soil structure interaction of a bridge abutment, right? So here is the abutment, as you can see, this part. And if you see the abutment wall has been modeled by this element, this form line, as you can see. So this is the abutment element, wall element, and this is the abutment footing part. Okay, the rest of the part is your soil. So on the back side of the abutment wall is your backfill. We all know that backfill material has to be there, just like a retaining wall. The abutment also has backfill, and then this is the underlying soil. And you need to model the soil up to certain extent on this side and certain extent on this side. Okay, and up to which depth you need to model, that also you have to establish. So depending on the soil layers, depending on where the rock is there, depending on the complexity, you have to decide. Now, if you see the kind of elements near the backfill and the abutment wall interface, you have small size elements. As you go away, you have large size elements. And you can see how you can transition using this kind of trapezoidal elements or triangular elements. You can make the transition. Okay. So similarly, just below the footing, this part can have more effects of the SSI on the abutment shaking. So once the waves come up, the soil gets shaken up, your abutment footing, the backfill gets shaken up, then the wall gets shaken up, and they mutually interact, right? So you need to figure out that up to what extent you are going to consider small elements. Because the more you have small elements in the model, the more complex will it be. So you can see how they have done the transition. Okay, this was part of a master's thesis work in IIT Kanpur quite some time back. Okay, as you can see, it was done by one guy in 2009, 16 years back, right? So I was that time also learning. I was doing PhD and also learning some of the things from him because it was very new to me. So he did a quite a good work, and then this is how the things look like. So if you are going to do the soil structure interaction and particularly do research, you should try to see that whether this continuum model can be established. Okay, if you do this continuum modeling, this is going to give you the most realistic result. See, whatever is the actual condition, exactly 100%, it can be never simulated. Okay, you should not think that my model is the best. There will be always some limitation, however sophisticated model will be yours. Okay, but then how far you can do the sophistication within the limited time frame, how close can be your realistic result, that is the challenge, right? So let me summarize. I tried to give you the overview of the modeling part, numerical modeling. So if you look at the soil flexibility, you have relief in the bending moment at the bottom of column. However, at the beam column junction, your bending moment increases. But you need to remember that that is not the soil structure interaction. That is only the effect of soil on structural behavior, right? So that is one part. However, when you have soil flexibility, another part is the increase of displacement, right? Sometimes if you have the soil modeled with spring or soil domain, the overall structure becomes flexible, right? So once it becomes flexible during earthquake shaking, your superstructure will vibrate, whether it's bridge, building, tower, whatever. So you have lateral displacement concern. You cannot sway the structure too much. You have a 30-story building and you consider sway at the top, and then people won't be able to stay there. Okay, so serviceability criteria comes an issue. Okay, so you need to have a trade-off, like how flexible your building can be. And then, as I mentioned, your time of computation, associated cost have to be always considered when you do this soil structure interaction study. And when you look for conventional buildings, small building, 3-story bedroom, 1-story flat, or something like that, it may not be affordable. Because if you have to do soil structure interaction for that one, you need to be paid by the client. Now, the homeowner, individual house owner, may not be able to afford that much money. Okay, so still for low cost, low budget projects, this may not be a feasible one. But for important structures like nuclear power plant, you have to do detailed soil structure interaction. There is no option at all. You talk to anybody in BARC or Nuclear Power Corporation in structural engineering, they will do that. Okay, because it's very critical structure and SSI matters in the response. Right? So that's all from my side in this presentation. So before I stop, I first must acknowledge the Assam Royal Global University for giving me the opportunity. And also I'm grateful to the Atal AICT scheme, Government of India, which also definitely is the sponsoring part. Okay. And then uh, all the things what I have shown you, I have learned from different students, whether they're doctoral student, master students, and so. So I must name a few: Shreya, Benazir, Nishant, MT, Devasmita, and they are all the master students who have worked on different structures. Aman worked on this soil structure interaction of underground station. He just started because that's a very new area. We have so many metro structures going on. So underground station, how does it behave? Being embedded in the soil. It's a different soil structure interaction. You don't have any superstructure above the soil. Everything is below, buried, right? So it's a different challenge. So I learned something from him also. And then my supervisor in MTech and PhD programs at IIT Kanpur, Professor Murthy, many of the things I learned from him, technical, non-technical. Now he's in IIT Madras. My collaborator in geotechnical engineering in my department, Professor Arindam De, with whom I have guided three students and also learning a lot of things from him. Professor Chinmoy Kole, he is now a faculty in IIT Kanpur, whose bridge abutment model I showed you. And then the Department of Civil Engineering, IIT Guwahati, where I work. Okay. Thank you for your patient listening. So please be feel free to have questions.
Thank you, sir. With this, I also ask the participants to take ahead the Q&A session. Actually, we would suggest that the participants would ask for the questions by themselves. So I request the participants to unmute yourself and ask your questions if you have any. And also the questions can be put in the chat box too, which I'll take forward.
Hello, sir.
Yes, please.
Uh, Sir, my name is Ninath Khandare. I'm assistant professor from Thakur College of Engineering. I
Yes.
just want to know actually because to know the soil structure interaction, so can we prepare a small model and can we replicate for the high-rise structure by preparing the small model of these soil structure interactions?
Uh, what I'll suggest is you if you want to go for this your spring model, what
Yeah,
I'll suggest is when you are learning the soil structure interaction, you
yeah.
can go for this BNWF model first, right? So
Okay.
in BNWF model, if your building is on piles, then this is the most suitable one. So there you can have a like the building can be low rise, it can be high rise, because here you are having only the piles and the soils model as springs, and these are modeled at certain depths, right? So in terms of complexity, this is the most simple. So if you are using BNWF model, you can
Okay.
use your full high rise building, maybe 25 story, 40 story, 30 story, whatever be it, okay?
Hmm.
On this BNWF model, you can use the full high rise one. However, if you are going for this continuum model, if you want to do that, here I
Hmm.
should suggest that you make a a small model, maybe of the building, maybe of 5, 6 stories, 4 stories, and then first learn that if you really give the here you need to give the motion at the bottom of the domain, okay, so that the soil elements will get shaken up, the waves will propagate through the vibration of these elements, and then wherever the piles will be there, the piles will be shaken up like that,
Mm.
okay. So
Okay.
whenever you are going for this continuum model, so here, my suggestion would be you go for 4, 5 story small rise building, and then you learn it. Okay. Once you are confident, then you increase it. Then you just replicate the stories, keep the model same. If you wish to keep the model same, no issue. But then you first do the learning part with a low rise building.
Okay. Okay.
Yeah.
Sir, one more thing, sir. You said some name of the book. So can you just drop in the chat box name of
Yes,
that?
yes. I'll write in the chat box.
Okay, thank you, sir.
It is Geotechnical Earthquake Engineering by Steven Kramer. The first edition came out quite early. I think it is by publisher Prentice Hall. Okay. So,
Okay.
and one edition, I think it came out either last year or the year before last year. That is the latest edition, right? So, that one, this is a very good book, Geotechnical Earthquake Engineering.
Yes, sir.
Yeah. So, I think I have another question from Praveen Thorat. Uh, when we are going to design structure as the strata is partially sandy and partially black cotton soil, what parameters would be taken in consideration while designing? Very good question, because whenever you have mixture of sandy and black cotton soil, and even in only black cotton soil, it becomes very difficult. So my suggestion is first you need to carry out the geotechnical tests for the soil layers extensively, like the extent of sandy soil, the extent of black cotton soil, up to which depth it is there. You need to have a number of boreholes and whatever requirements are there. Once you assess that, what kind of foundation you have to go for, that has to be consulted with some good geotechnical engineering person. So the structural engineer as well as the geotechnical engineer should sit together and decide. Okay, if it is happening that you have a high rise building and lot of loads are coming, the piles are coming out to be very uneconomical, you need to have a pile raft over a large extent, because you have black cotton soil settlement and so many things are there when it becomes wet, and there can be a lot of changes in the soil. So we structural engineers, we are not at all expert in that. You need very good competent geotechnical person. Okay, somebody who has extensive experience on this. So you need to consult them. So if the foundation part with the soil conditions as they are, if it is coming out to be very uneconomical, probably your ground improvement by some technique may reduce your cost. Your ground improvement may come to be economical. Okay, it depends on the extent of the sand layers, black cotton soil, and so on. So that is my only suggestion. Okay, so before going for design, you need to assess those things very carefully, right? So that's what my suggestion is. What parameters would be in consideration while designing? Like it depends. If you are going for pile foundation, you know the parameters for which you have to. So for pile design, there is one part involving the geotechnical parameters by which you find out pile capacity. The other part is your structural design. Okay, when you do the structural design, it is just like you have a circular section subjected to shear force, axial force, bending moment, and you can use the interaction curve, PM interaction, or any kind of interaction curve at design level for the design. That is for the structural part. For the geotechnical part, you have the different parameters, whether how much it will it be resisting through end bearing effect, how much will it be resisting through skin friction. So all those things can be decided. Okay, so that's why you need to consult a geotechnical expert in that domain, right? Then I think we have a question. Can you tell about the future scope for carrying out research in this domain? There is unlimited scope, what I can see. There are so many structures nowadays coming up in soil, in rock, in partial soil. There's so much research to be done. You talk about tunnels, okay? Tunnels are being built everywhere, whether it's below seabed, below river, in through rocks in hills or through normal soil. So tunnels will have different soil structure interaction behavior for different cases. Okay, so there is immense scope. You talk about any buried structure, because nowadays in defense, many of these army establishments, they are going for many of these buried structures. Okay, different kinds. So a lot of scope of research is there. And then if you are talking about the conventional ones, say buildings, bridges, many things we are yet to learn, right? Pile soil interaction for different kinds of soil. There are so many things. Marine areas, when you have piles on which jetties are built, you have the wave action, you have the soil action together, coupled action. There are so many challenges. You can just think and you can decide, right? But then when you are going to do research, you should have some area in your mind, like you need to study the literature, that what are the things work in one particular area. You have to choose some area of your passion, some interest, and then you need to study that whatever work has been done, you have to build upon that, right? So based on that, you have to decide whatever is your scope of research. Okay, but then unlimited scope, lot of things are to be done. Okay, lot of things have been done also, but yet to be done, so many things I can think of, right? And then, yeah, so this is Snehal's question: how the interface between the structure and the soil is modeled, the connection between the two. Okay, very good question. So when you have the pile and the soil, there has to be one interface element. So what we do is we model the pile, and just at the same location we have the soil nodes also, right? So between the soil node and the pile node, physically the soil node and the pile node, they are on top of each other, they are at the same location. So they are connected by a small element which is of zero length. Okay, so you have the pile node and you have the soil node. So physically, if you see the coordinates, they are one on the other. Okay, but between the pile node and the soil node, there is an element which we consider of zero length, and that element has to be assigned the properties for that interface. So depending on the type of soil, depending on the pile surface, okay, your interaction part, that will be affecting, right? So in the particular program called OpenSeas, you have your uh, this contact property, where you can model this friction, where you can model the normal impact. Okay, so you have certain parameters to model that contact and the friction. When you have pile and the soil is of sandy, cohesionless kind, when the pile tries to move away, the sand or the cohesionless soil will try to follow it, right? There won't be any gap. So when the pile is vibrating along with the vibration of the sand during earthquake shaking, always the pile and the soil, the sand, they are in contact. Okay, so in cohesionless soil, the sand will always follow the pile. Same with the backfill, like when you have the bridge abutment and the backfill, if the backfill moves away from the abutment wall moves away from the backfill soil will try to follow, because generally backfills are having compacted cohesionless soil, right? But then if you have clay soil, what will happen? Your sudden movement of the pile away from the soil may create a momentary gap, because clay soils, they are cohesive, they tend to remain together. So when they are in contact with the pile and the pile suddenly moves away, there can be a momentary possibility of gap creation. Okay, so that interface zero length element needs to be assigned these properties. So depending on the type of soil, the properties have to be assigned, right? Okay, then Niranjan Bora. I think Niranjan was our student. I'm not sure whether it's our student. The same student, Dr. Abhishek Kumar. So I have a question regarding ground motion application during soil structure interaction analysis using the continuum approach. How and at which location are earthquake ground motions applied when the soil model volume is large and many meshes are involved? Okay, so let me go back to that slide. Right. So here what happens when we are considering the earthquake ground motions, you have this pile model as the beam column element. You have these spring and the dampers at the different levels. Okay. So when the ground motion is to be assigned, we assign them at the ends of these springs or the ends of the spring damper system. Okay. How are the ground motions obtained? The ground motions are obtained through this free field response. We first do not consider any structure or foundation, just model a soil column, and then we shake up the soil column by means of the rock level ground motion or the underlying ground motion. Okay, so the once the soil column gets shaken up at different levels, okay, the property of soil will modify the underlying ground motion, right? Whatever has been the input. So at different levels, depending on the soil property, through that convolution mechanism, you get the ground motions at different levels. Okay. So those ground motions will have different frequency content, maybe different amplitude content, depending on the soil strata, right? So in your this one, sorry. So basically your question was that at which location the ground motions are applied. They are applied at the those spring locations, spring dashboard locations. Where you want to apply these springs at which depths, that depends on you. Basically, the way we discretize the pile into number of elements, at each node we connect the spring damper system. So at those levels, once you decide that where the piles uh, are going to be discretized, the nodes are to be located. Once you know the depth, at those depth, you extract the ground motion output from the free field response of your soil column, right? So that's how you can do that, right? Fine. And then when the soil model volume is large, how many meshes are involved? Okay, so that is for the spring part. Now in the continuum approach, you have to apply the ground motion at the bottom of your soil domain. So if you look at this one, the soil domain is limited here. So at this level, the ground motion is applied. Okay. And when you have the ground motion applied at this level, you need to have this spring dashboard system because you cannot have fixed end. You need to have absorber boundary. So when you have dashboard, you have to apply the ground motion as velocity time history, not the acceleration versus time, right? So you need to apply here at this location. And then depending on the volume, it doesn't matter. However large your domain may be, once you apply the ground motion at this bottom level, depending on the soil property and depending on the ground motion, it will propagate, get convoluted, and at different levels, you can get the ground motion output. But then always the ground motion output at different levels, you can get for the free field case. You should not consider structure and the foundation. Okay. Uh, Bonisha has asked, what are the available codes for analyzing structure with SSI? Well, if you look at the Indian standard, IS 1893, your design response spectrum has the curves for three types of soil, as I mentioned. So uh, you can have in the design procedure the codal provision incorporated having the effect of soil or SSI through these curves. So that is the most simplified way. Otherwise, for conventional buildings, we do not have codes or codal provisions for specifying SSI, because when you have to go for SSI, you need ground motions. And then what are the ground motions you have to apply? That is the challenge. Because when we design any structure, we never apply ground motion, because for which ground motion you are going to design, it's debatable, because whether that ground motion will be at all occurring during, or that can be the maximum effect, you never know. So for real SSI, you need ground motion, and with ground motion, it's difficult to design. So directly, the codes do not specify SSI. But yes, if you look at the design guidelines for critical structures, suppose nuclear power plants or dams, so there they specify that SSI is mandatory, and there you have to carry out the seismic hazard analysis to a certain detail to get the ground motions, right? So again, there, for the design is done by equivalent static method. Then you have to do the seismic evaluation multiple times depending on the possible ground motion. Probably if you see if the ground motion are giving you quite large shear force and bending moment as compared to the design values, maybe you have to magnify or scale up the design moments and shear force. Okay, so there are different aspects involved in that. So for critical structures or such lifeline structures, certain design guidelines are there about SSI, right? But for conventional buildings or bridges, you don't have specific codes related to SSI, because the uncertainty associated with the ground motion uh, limits this provision, right? Okay. Yes, definitely you can get in touch with me for further clarifications. Yeah, I think that's all for the questions.
Yes, sir. I
Yeah.
That is all for the questions, sir. Before we start the second session, would you like to take a break?
Yes, I think I'll just take a break of 5 minutes, 5, 7 minutes. Will that be fine?
Sure. Of course, sir. Of course.
Yeah.
I request the participants to be there while we start the second session. We'll take a break of maximum 10 minutes.
Yeah, sure. Thank you.
Thank you, sir. Yeah.
Thank you.
Dear participants, please be there with us. We will resume right after sir comes back. And I hope you have all filled your attendance sheet. Please be there with us. Right before we start the second session, we will take the photograph for the attendance purpose.
I think we can start now. Our speaker has joined.
Okay. But before we start, sir, with your permission, can we just take a moment to take our attendance record with our
Sure.
participants?
Sure. No issue.
I request everyone to please turn on their camera so that we can take the attendance for record. Jay? Jay? Are you there?
Yeah, Jay is not there, I think. I have taken it.
Okay. Have you taken it all?
Yeah, I think we can.
All right. Thank you so much, sir. And thank you, everyone. You can turn off your cameras now if you want to. So we can start with your session now.
Okay, let me share the screen. Yeah. Is my screen visible?
Yes, sir. It is.
Yeah. Just wanted in the slideshow mode. It's taking some time. Let's do it. Okay, let me start here. The slideshow mode is probably taking some time. Okay. Is my screen visible? I think this is fine.
Yes, sir, it's visible.
Yeah. Anyway, so let me start. So welcome once again. So this is the second topic. This is the importance of floor slab in seismic behavior of RC structural wall in frame wall buildings. Okay, right. So this is the overview of my presentation. Again, I'll spend some time in introducing the topic. Then we will look at observations from past earthquakes. Then how the modeling is done, and then how the structural analysis is carried out in this case. Then what are the salient outcomes? Not all the results will show, and then we'll summarize. Right. Fine. So with the introduction, let me just start the behavior of what exactly is the role of shear walls. Okay. So as we know, in the typical multi-story building, what we see around in urban areas, we have the frame structure consisting of the columns coming up right from the foundation, and then we have the beams completing the framing action. Then you have the floor slabs, right, at different levels, and we have the roof slab. Then once the frame is in position, we have the infill walls, maybe from burnt clay bricks or from nowadays the autoclave aerated concrete blocks, the AAC block walls. Okay, so these can be different ways. Now what happens uh, when we have this building coming up in earthquake prone region, so what will happen? Again, the waves will come up, shake up the foundation, the vibration will propagate first through columns, then the beams, floor slabs, they will be all shaken up and they will be interacting as we discussed in the previous one. Now, if we want to build a building, say more than 6 stories, 5 stories, 6 stories, okay, in severe earthquake prone region where you have quite large seismic hazard, okay, so in that case, we find that whenever we try to design against the maximum possible earthquake effect in terms of the design lateral loads and combine the effects with other loads, dead load, imposed load, and so the sizes of the columns and to some extent sizes of the beams, they not turn out to be very large if the building height is exceeding 6 stories or so. Okay, what is the reason? Basically, when you look at the requirement, when this entire frame is getting shaken up, swaying back and forth, you require some elements to minimize the drift or the sway, because only beam, column, and slab, that frame is on the slender side. The flexibility is large. So once you have a bit high level of shaking, it will tend to sway back and forth vigorously. So when you are looking at somebody on sixth floor, seventh floor, or eighth floor, the person is going to experience quite a level of shaking, and it is extremely discomforting and scary. Okay, so that is one part. That is from the perception point of view. If you look at the behavior of certain belongings or elements inside the room, they can also get damaged, like your beams, columns, walls. These are part of the structural system. Suppose the top floor or the top 2 floors are housing certain laboratories, okay, maybe having chemicals and many other things. So they can have apparatus, glassware, plasticware, breakable items, and so on. So if you have large shaking at the top level, those are likely to fall down, get damaged, and incur economic losses. So what are these elements? These elements are known as non-structural elements, okay, which do not participate in the structural behavior. Okay, so of late, the last 2 3 decades, uh, securing the non-structural elements so that the financial losses are minimized, that has become a widely researched subject. Okay, many people are doing research on that. Especially nowadays, people are more focusing on the economics part. Structural damage, repair, rehabilitation, strengthening, that is one side. You have a lot of non-structural losses which may lead to more economic effects, right? So those need to be minimized. So you need some elements which will minimize the sway of that slab beam column building. Also, when you have large shaking, large ground motion is there, the shear forces generated at different levels of column, they are also large. So your sizes of the columns are required to be large. They need to be more stronger. So people have thought that instead of the column, which is having 2 dimensions in plan on the smaller side, why not extend one of the dimensions of the column to a long extent? So you have 1 dimension of the column fixed, the other dimension you extend. Okay. So if 1 dimension is say 300 mm or 400 mm, the other dimension you make it 4 meter, 3 meters, something like that. So between 2 columns, you are now having an element which is spanning from one column to the other, made of reinforced concrete. Okay. And this is going to come up right from the foundation up to the top roof level, right? So this is the concept of your reinforced concrete wall, right? So how will we build it? You have the reinforcing bars in the columns at the 2 ends. You'll put the vertical reinforcing bars in the walls. You'll put the ties in the columns, right? The transverse reinforcement. So along with the ties, you'll put some horizontal bars because we have extended 1 dimension of the column. So you'll put horizontal bars in the wall. So all are being done together. So concrete will be poured right from the bottom to the top with different stages in both the end columns as well as the wall, right? So reinforced concrete wall is going to be monolithic in action along with the two end columns. So sometimes these two columns are called boundary elements because they define the boundaries of the wall, and this is the intermediate wall. So why are we thinking of extending the column dimension to make a wall? Because once you have one dimension large, there are two effects. One is the large lateral stiffness. How do you define stiffness? If you recall back what you learned in your undergraduate structural analysis course known as the matrix method, right? So in matrix method, you define a member with nodes, define the degrees of freedom. For each degree of freedom, try to find out stiffness element. Those elements will populate the member stiffness matrix. Now, if you have a beam, you have a column, you have multiple such members. For each of them, you have member stiffness matrix. And then you transform the member stiffness matrices into global coordinates, do the assembly, get the global stiffness matrix, apply the loads, analyze and get the displacement. That's how the structural analysis work. So your stiffness elements, they have a term called I, right? The elements associated with shear, bending, they have I. I is the second moment of area, okay? And more specifically, E times I. So you have elements like 12 EI by L cube, 6 EI by L square, 4 EI by L. So what is E times I? Modulus of elasticity times second moment of area. That is called flexural rigidity. It defines how flexurally rigid or flexible a member is, right? So when you write the simple beam bending equation, bending moment equal to EI times d2W dx2, that simple beam bending equation. So there also the EI comes. The more the EI for a specific d2y dx2, you have large moment, right? So that is also the basis of the moment curvature relation. d2W dx2 is the curvature, right? So anyway, so this flexural rigidity term has the parameter I. I for a rectangular section is width times cube of the depth divided by 12, BD cube by 12 for the major axis passing right through the depth, right, mid part of the depth. So in the wall, if you consider this as the D, right, and the thickness of the wall as B, D is very large. So thickness may be 200 mm, 300 mm, and D may be 4 meters, 5 meters, something like that. That is column to column spacing in the building grid, right? So when you have such large D, BD cubed by 12, the escalation or enhancement is manifold. It increases as cube of D. So if D increases by large amount, D cube increases much more. So your I value for the wall about the axis passing through the middle of the section, centroidal axis, that is very large. So when you have in plane action, right? So when the wall tries to bend like a cantilever column in its own plane, you have large I. So the wall is very stiff. So when you have large earthquake shaking at the bottom, right, starting from the foundation, and the entire building frame tries to sway back and forth, these walls being very stiff elements, large EI, they will restrict, right? They won't allow the building to sway too much, right? If the wall was not there, you had only columns, the EI of the column is very less because I is small as compared to wall. I for column is very small. So EI is very less. So your flexibility is more. The column will sway, but the walls will not, right? So your wall will arrest or restrict the sway by virtue of the large lateral stiffness. Now, second part is large lateral strength. How do you define strength? It is like shear capacity, right? In a section, when you have these horizontal earthquake forces, okay, all the floors are trying to move with respect to each other in different directions. So at different levels, you have these walls and the columns subjected to shear forces, and they are getting transferred to the foundation and underlying soil. So when you look at this shear force, how much this wall section can resist, that's the shear capacity. If you recall, how do you find out the design shear capacity for a reinforced concrete section. As per IS 456-2000, it is like total shear capacity is partly by concrete and partly from steel, VC plus VS. So in VC, you have the term that tau C, design shear strength of concrete, right? Table 19 of IS 456-2000, depending on the longitudinal reinforcement ratio and the grade of concrete, right? So tau C is one parameter. B, that is the width of the section, is other parameter. Third one is D, effective depth. So effective depth will be, of course, related to the overall depth also. So in the plane of the wall, in its own plane, where you have the large D, the effective depth is also large because you have the vertical bars. You can find out the effective depth. So tau C BD, that term for the wall will be large. B is small, same as the column, but D for wall is much larger than the column, right? So your shear capacity for the wall will be more than the shear capacity of the column. So wall can take large shear force, and wall is stiff. We what we discussed in the last presentation. Once you have a stiff element, it will absorb all the forces. Once you have the flexible element, it will release the forces. It will move, right? So walls will absorb or attract more shear forces when you have the earthquake shaking as compared to the columns. So when you didn't have the wall, you had only the columns. Your columns would have been subjected to large shear force, each one of them. Now, with the presence of the wall in this direction, along this direction of the building, okay, this wall will absorb most of the shear forces. These columns will not be subjected to that much shear force, right? So the columns are getting less damaged due to the large strength of the wall. So large stiffness, large strength, these are the two important virtues of the shear wall. So in earthquake-prone regions, when you have multi-story buildings with the number of stories exceeding 6, 7, 6 onwards, we generally provide walls. Okay, till which height? If you have 100-story building, if you have 150-story building, will shear wall work? It will work, but then just like column, if you have a 100-story building, the sizes will be enormous. You may need a wall of 2-meter thick. So 2-meter thick wall going up to say 50 stories, and after that you have 1-meter thick wall up to 50 100 story. It's not at all economical. Okay, so many things are there: mass concreting, shrinkage, temperature, so many things are there. So beyond 30, 35 stories, shear walls are not economical for structural system in high-rise buildings. So from 6 to 30, 35, this is the range where these walls provide very good uh, stiffness and strength and provide good earthquake resistance for these frame buildings. Okay, so that's the basis of this shear walls. Okay, so in general, it is reinforced concrete wall. Since it absorbs large shear forces, it is very commonly known as shear wall, RC shear wall. Since it is helpful in the structural arrangement and you carry out special earthquake resistant detailing for this, we also call it RC structural wall, right? In IS 13920-2016, the Indian code for ductile detailing of reinforced concrete structures. So it is called special walls, right? Because they are specifically designed for earthquake resistance. If you look at IS 456-2000, there also you have a section on design provisions of reinforced concrete walls, right? So they are normal reinforced concrete walls. They are not designed against earthquake resistance. They are not detailed against earthquake resistance. Okay, so you should never consider an earthquake resistant shear wall to be designed as per the provisions of IS 456-2000. Okay, never. That is for non-seismic design, non-earthquake resistant detailing. Right? Fine. So with this introduction, let us move to the force transfer mechanism. So how does the force get transferred? So you have the slabs at different levels. As we know, during earthquake shaking, the lumped masses are at these floor slab levels. So during shaking, the masses get accelerated. So once the masses get accelerated, we know the generated force is proportional to the mass. Right? Okay, mass times acceleration. So in simple way, at different flow levels, whatever forces are generated, they are transferred through the walls, okay, to the foundation and the underlying soil. So at different flow levels, the walls keep on receiving the forces, and then finally the total base shear is transferred to the bottom. Okay. If you have columns, they will also transfer some shear force, but since walls are stiff elements, they will attract the lion's share of force. So most of the forces will be passing through the walls. What about the direction? This wall will be effective in resisting shear and providing the stiffness along this direction in plane. Along the other direction, this wall, how much is the D? Now the width of the wall becomes D. So BD cube by 12, B becomes this and D becomes the thickness. When you are considering the other direction, that is the length of the building, for this wall, now the thickness becomes the depth, right? So when you have BD cube, now the D becomes the thickness, very small. So in the out of plane direction, in the other direction, this wall will not be effective in absorbing the shear force. The stiffness is very small, I is small. Okay. So in the other direction, you need separate walls, which will be having the in-plane configuration in that direction. So if you have shaking in this direction, force is applied in this direction, this wall will be effective. If you have force in this direction, this wall will be effective, right? So you have to position the walls accordingly, right? So this is the transfer mechanism. And then let us come to the classification of walls. So first one is the slender wall, where you have this height of the wall divided by the length of wall more than 2. Okay. How will it behave? Here, as you can see, it is like a cantilever beam turned upward, right? In a cantilever beam, you have the horizontal beam, you have one restrained end and the other free end. If you turn it anti-clockwise 90-degree, this is your fixed end and this is the free end. So this is a long member, so it will act like a vertical bending beam. So vertical cantilever, it will simply bend like a cantilever. Now, since the length is more, it will bend. So flexural strength will govern. The action will be like a beam bending, right? Just a cantilever beam bending in the vertical plane, right? So that is called slender wall. And this is one figure of a slender wall. This was taken in University of California, San Diego, where they have a large outdoor shake table. Shake table is a table on which you can mount any model of any structure or any component and shake it, give it the ground motion like what you experience during an earthquake. So that element will be subjected to that earthquake motion, and then they will study the damages and behavior. So this is one slender wall constructed. As you can see, the height is very tall, okay, and as compared to the length. So this is for slender wall. Then you have the other category where H by W is less than 1. That is called squat wall. So in squat wall, what will happen? If you have any lateral force, horizontal force, since the height is small, it will not bend. How will it deform? It will deform like as if it is being sheared. So it will deform like a shear action, right? So if you again turn it clockwise by 90-degree, you will get a cantilever beam, which is deep, right? Which is very deep. So when you have a deep cantilever beam and you apply the load at the tip, does it bend? It doesn't. It simply shears, right? It will have a shear deformation. So similar to that, squat wall will also have shear deformation, and the flexural deformation will be very less. So they act as vertical shear beams. So here the shear strength becomes the criteria. Okay. Now what happens to the range H by W between less than 1 and more than 2? That we call as intermediate walls. If you look at that IS 13920 specification, the intermediate walls. So you have a mixed effect, flexure and shear together, right? So it's difficult to figure out the behavior of that. These two ends are easier. Right? Example, you have a lot of such squat walls as bridge piers. Okay, this was taken from a bridge in the region of Sikkim. So as you can see, the height is small and the length is large. So although we don't call them walls, they are squat piers. right? The same squat word is used, but these are squat piers. So when you have the shaking, you have the horizontal force and they will act in that form, right? Right. So let us see a few failures of these structural walls from the past earthquakes. So if you have some weak layer during construction and during earthquake shaking, you can have crack developing that can lead to horizontal crack at construction joint. So there can be a possibility of sliding, small sliding, as you can see here. So this happened in Chile earthquake in 1985. Sometimes if you have this underlying soil layer a bit weak, you can have this kind of rocking action. So in rocking action, what will happen? Initially, there may be cracks, but then this foundation, this footing will get tilted. Okay. And during back and forth action, this foundation will keep on rotating. So that is called rocking. Okay. So rocking stiffness we talked about during the lump spring model in the previous presentation. So this is one rocking failure. So above the ground, you may hardly see any damage, but you will see the damage below because the damage is primarily here. So there was some paved area. So the paving area also got damaged because the underlying soil underwent some changes. Then you can have out of plane stability. So this is the wall. These are your vertical rebars. These are the horizontal rebars. So what happened was when you have this, say, 25-story building, on the wall you have large compression coming, right, from those so many floors. The thickness of the wall has to be checked against out of plane stability, kind of similar to buckling. Okay, in buckling, what happens? You apply the compression, and if the member is slender, it suddenly deforms laterally. First, it undergoes axial compression, then suddenly it deforms. Okay, so that is buckling. So this is not exactly buckling, but then since it was under compression and due to less thickness, since the cracks were already formed, so similar kind of instability in out of plane direction developed. Can we use this one? No way, because as you can see, along with the failure, this out of plane action, lot of concrete has spalled off. Okay, rebars have bent, so you cannot use this, right? So this happened during 2010 Chile earthquake. So then you have these kind of severe failures. So in the boundary element, if you have large amount of uh, cracking, then what will happen if the concrete goes away? Like the inner core concrete also got crushed. Now what happens during large shaking, the rebars, they are not having surrounding concrete, nothing to hold it back. So in that case, you can have this kind of buckling of rebars. The concrete has entirely gone away. Okay, there's nothing to hold it back, restrain it back. Earlier it was having cover concrete, core concrete surrounding it. So now with large compression, the bars can buckle. If sometimes if you have the bar quality of poor nature, okay, they can fracture. Okay, this is quite unusual. It can fracture. So here it has fractured. And then of course you have the bar buckling as well as the shear failure has also happened. You can see the shear cracks like that. Okay, so these are very interesting failures of this. And then of course, when you have shear walls around the lift or elevator, okay, you can have the diagonal cracks. This was observed in number of buildings during 2001 Bhuj earthquake, right? So in the bottom part, you have the shear effect. Even if the wall is slender, the bottom part will have the boundary region effect known as D region, disturbed region. So there you can have the shear crack. In shear crack, what happens? In whenever you have shear, you have diagonal tension, diagonal compression. So concrete will first crack, forming the diagonal shear cracks. Then it can get crushed when it gets reversed, and so on. Now here is very interesting. Here you have the wall, and here you had the slab, right? Generally, when we talk about earthquake resistant design, we don't talk about the earthquake resistant design of slab, right? Because beams and columns, these are the elements which are supposed to be undergoing damage during the seismic action, right? So we talk about ductile detailing, earthquake resistant design for those elements. Slabs are generally kept aside. They're not supposed to get damaged. Here, the entire slab wall junction got damaged. during earthquake shaking. Maybe the damage started in the wall, but then it propagated in the slab, right? So that was the uh, interesting part. So this gave a deep insight that even the slabs may not remain undamaged. Okay, and this, since this happened, many of the time we ignore the slab damage, right? So this was also observed in the 1985 Chile earthquake, which was kind of eye opener. So this damage at wall slab junction, since it was observed in 1985, so this became an interesting one. In uh, different failures of shear walls, these two Chile earthquakes carry a lot of significance. Chile is a country where they have quite improved provisions for design of shear walls. Okay, since Chile is an earthquake-prone country on the Pacific coast, on the lower side in South America, they have earthquakes keep on coming, small, large magnitude. These two earthquakes were of particular significance because many high-rise buildings which were having shear walls designed as per the established provision, perfect ductile detailing. Many of them underwent different kinds of failure. So just like the Kobe earthquake did a lot of change in the design of these viaducts, flyovers, bridges as per Japanese codes, these two earthquakes made Chile earthquake engineers think and formulate new provisions for shear walls in buildings. Okay, so that's why these two earthquakes are very important, right? So 1985 earthquake, there were other observations also at slab wall connections, right? So the concern is that these stresses developed at the wall slab junction led to that damage. So the presence of slab is perhaps influencing the performance of wall. What, when we talk about slender wall or squat wall, there was no slab, right? The wall was bending like a perfect cantilever. So in between, we don't have damages that much. We always think the cantilever wall will have damage at the bottom due to large bending moment. But then when you have the floor slab connected at different places along the wall, so those regions are showing damages as we have seen. So in the seismic design of wall slab junction, do we need to change our philosophy? Do we need to rethink or relook at? When we do the earthquake resistant design of any building or the components, we carry out two levels of design. One is the limit state method, conventional one. Generally, for normal buildings, residential buildings, we only design against limit state of collapse, right? As per IS 456/2000. Okay, we rarely consider limit state of serviceability, but for certain buildings or certain structures, we have to consider. And then once you are arriving at the dimensions, rebars, and all the things as per limit state design, there we do linear elastic analysis with design node combination. Then we have to do the second level, that is the capacity design, based on the possibility of the actual behavior. Because when we do the limit state method, we consider load factors, we consider partial safety factor for materials. Both are idealized cases. We are reducing the strength, we are enhancing the load with some probabilistic basis, and then doing the design. When earthquake is coming and striking the entire structure, the material in the building, material in that structure doesn't know about partial safety factor. Whatever way it has been constructed, it has been cast. The material will behave like that. So this actual behavior of material can lead to higher forces than we estimate at design level, at the limit state design level, right? So that is the concern. It's very well illustrated in IS 13920/2016. So that is capacity-based design. And then we also look at the sequence of possible failure modes. We segregate into ductile failures, brittle failures. We want the ductile failures to occur first so that the entire behavior is ductile and so on, right? So that's how we do the capacity. So both these are mandatory. In none of the places, especially the second one, the behavior of slab is considered. Never it is considered, right? So then comes the study. So one of the participants here, Snehal, it is based on her work only. So her results only I will show. So it's very nice to see her here. So in the question answer session, she can also add a few points. Fine. So let us come to the modeling first. So how are the modeling techniques established? So you can have macro modeling of the wall, right? So in the macro modeling of wall, you have this entire wall between the two columns or the boundary elements replaced by a frame member located at its center line. Okay, right at its center line it's located. So this entire property, see, when the wall is constructed along with the columns, they are going to be monolithic. Generally the column dimensions are slightly larger in width, wall thickness is small, however the length is large, so it looks like an I section. As you can see here, these are the boundary columns and this is the I section, right? So this is the wall part, these are the end elements. Sometimes we have the similarity with the flanged section for a steel flanged beam, steel section, structural steel section. We call these two as flanges. We call this the wall body as the web. So these two terms are also there, right? So when we are replacing this entire wall and the boundary element part with this element, so this element has to be given the properties of this I section. Now, between these two beams at this floor level, the wall was there, right? So between these two beams, the wall was there. So now if you consider only this element, how does it get connected with the beams? Because in reality, the wall was connected with the beams at every floor level. So what is done is this element is like a frame element assigned with the properties of the I section. However, at every floor level, we connect two elements like beams which are very stiff, which are rigid links. Maybe the modulus of elasticity is assigned 1,000 times of that of concrete. So what is the purpose? Why do we assign these rigid links? Because when this entire assembly is going to bend, right, the rigid links and the member, they will bend together. So when this will bend, the rigid links will also bend along with that. So that kind of cantilever action, which you expect in the actual wall, possibly will be mobilized in this way. Okay, so you need the center line wall element with the assigned property of I section as well as the rigid elements. So the cross sections of the rigid links can be given anything, just like the other beams, but the modulus of elasticity has to be very high. So this is the equivalent center line modeling or equivalent frame model of the wall. This is the most suitable model if you have to carry out this nonlinear static analysis of wall. So when we do the seismic performance evaluation, we do not restrict ourselves to the linear elastic analysis because we need to see the damages. So in that case, all the inelastic behavior can be assigned to this frame model very conveniently. Okay, so this has certain things. You can carry out the design of the wall also in the linear elastic analysis. You can do that, but nowadays all the programs have the provision of extracting the design shear force, design moment at different levels if you model the wall using the shell elements. Okay, so that also is there. So the other type of model which is very commonly used, that is fiber model. What is fiber model? When you have a wall cross section, you define this wall by means of different fibers across the section. So if you have a wall like this, wall portion like this, as you can see here, this L shape, you are uh, discretizing this entire cross section into number of fibers. So these are your concrete fibers, small ones, and these red ones are your rebars, steel reinforcing bars. So these are also fibers. These fibers run along the entire height, the concrete fibers and the steel fibers. What are the properties assigned? So this is like kind of micro modeling, because you are now looking at assigning the individual stress strain curves for the concrete and then for the steel for your rebars, right? So you can go like this. So this is for the steel, this is for the concrete. So each fiber response is monitored by the program when you do the analysis, and then you can get the response. Okay, so this is kind of micro level modeling for the wall. And then you have the finite element modeling, right? So in finite element modeling, as we had seen for the soil domain, you discretize into number of fibers. Here If you want to model a wall along with the floor slab, you have to use solid elements. Solid elements means 8 noded elements. There are 4 nodes in one face, 4 nodes in the opposite face. So 8 noded elements with only the translational degrees of freedom. Okay, you have to use that element for modeling them. And then inside these elements, you can embed the steel reinforcing bars. You make this cage of rebar separately, these parts separately, and bring this entire rebar cage inside this, so that at appropriate locations, the nodes of your concrete and the rebar, they are tied, and then it's done. Okay, so this was done using the finite element program Abacus. Okay, so it was part of the validation thing. So this was the use for rebar. We use truss element. That is what we use generally. So the truss element will give you axial forces because the rebars will have tension or compression. Right? So that's how we do the finite element modeling. So 3 different levels of modeling. One is the macro, the second the fiber, then the actual finite element modeling. So these 3 are the common methods how you model the rebars or the slab wall connection, right? Fine. Then let us look at the methodology. So when you use the 8 noded solid element and you want to use the uh, entire assembly for nonlinear analysis where you expect to get damage, so you need to use one model known as CDP model, which is called concrete damage plasticity model, right? So that is one model, and this is the kind of element, 8 noded solid element. Now if you are familiar with the finite element method, how the numerical process works, there are certain shape functions which you have to define, and the shape functions have different polynomial forms, higher order polynomial, less order polynomial. Okay, sometimes in order to reduce the computational effort, we look at the integration at a lower level. So that's how the term reduced integration comes into picture. So in any element of abacus, if you have this capital R at the end, that signifies that this particular element takes care of the reduced integration, less computation by certain way in the polynomial form. Okay. And then you have 2 noded truss element as reinforcement. So you embed it, as I mentioned. The work which I'm mentioning here did not have any interaction with the soil. It was not carried out as nonlinear dynamic analysis like applying ground motion and so. It was done by nonlinear static analysis. What is nonlinear static analysis? Also known as pushover analysis. You just sway the structure or push the structure in monotonically in one direction and then see with large lateral displacement how are the damages and those things coming up, right? So that's how it's done. Since soil was not considered, all the degrees of freedom were restrained at the base, as I had mentioned earlier, right? And since we are looking at the in-plane behavior, the out-of-plane behavior of the wall was also restrained. Okay. So this is how the elevational section looks like. This is how the cross section looks like. When you have the wall with the sizes of your boundary element same in the width direction, this looks like a rectangle, and these are the vertical bars and the horizontal bars in the web part. This is for the flange. Okay, sometimes if you have less thickness, say 150 the code allows to provide single layer of vertical bars and single layer of horizontal bars. But whenever you have wall thickness 200 or more, you have to mandatorily provide 2 layers of bars. And then this is how the concrete also has been discretized. You have the end nodes, which are the truss elements, and then you can have the intermediate nodes as concrete elements, because in 200 also you can have multiple concrete layers. You discretize depending on number of elements. Very importantly, the confinement actions need to be taken. What is confining action? Whenever you have these end columns, right, end elements, when the wall is connected to bending moment, one part will be under tension, the other part will be under compression, right? Now, when you have compression, your concrete in that part comes under triaxial stress condition because you have ties, okay, which are going to hold back the concrete under compression against bulging. So you have confining action mobilized. So confined concrete has higher strength than the cover concrete. What we use in IS 456 2000, design stress strain curve, flexural compression, 0.45 FCK, they are more close to the unconfined concrete, no confining effect. Okay, but in reality, when you do the actual behavior, confining action is bound to come depending on the spacing of your ties at the end regions, right? So as I mentioned, the concrete damage plasticity model has to be considered for concrete. This takes care of degradation of strength and stiffness. Because when you look at the behavior of concrete, as you can see here, the concrete, if whether it's unconfined or confined, first it picks up strength and then it reaches a peak value, then drops. So this part is the ascending part where it is picking up strength. This part is the degrading part. So the strength degradation reflects or captures the damage. Once it tries to degrade, once it goes in degrading part, that means the damage gets started, right? So whether it's confined or unconfined, the damage will be there. So this degradation of strength, slope also, the stiffness also degrades. When the concrete becomes weaker, it becomes less stiff. So that is captured nicely by the CTP model. Okay. And then when you talk about reinforcing bar, you have the normal reinforcing bar stress strain curve going for the design part like 0.87 FY, what we use as per IS 456 2000. But then we are looking at the actual behavior, right? So in actual behavior, we need to consider the stress strain curve, what you get during the uniaxial tensile test in any UTM machine. Okay? All of you have seen in structural engineering laboratory under universal testing machine UTM, if you take a coupon of a steel reinforcing bar and you pull it, how the stress strain curve looks like. So after yielding, it generally picks up strength known as the strain hardening effect. Okay, so this ultimate strength is higher as compared to the yield strength. So while designing, we are considering 87% of the yield strength, 0.87 FY, whereas during actual shaking, the rebar is going to follow this stress strain curve. So depending on the strain level, the strength is going to be higher. Okay, so all these need to be considered in the actual behavior when you consider the nonlinear analysis. Right? So these are some of the aspects, mainly the cracking and the crushing. So under tension, concrete is very weak. So how the cracking stress strain curve is modeled. When under compression, it is going to get crushed. You have more capacity. So these are the primary failure mechanism. And then you have two damage variables, DT and DC, which signify the damages. So you need to assign the parameters depending on the modeling, okay? And that will facilitate capturing the damage when you use the CDP model. Right? So this is well-established model. There's nothing new about it. There are different parameters starting from modulus of elasticity. You have these particular parameters, these last five parameters, starting from dilation angle, eccentricity, viscosity parameter, shape factor, stress ratio. These all are part of the concrete damage plasticity model. Okay, these are CDP models. Fine. So when we try to validate, first we try to establish that what are the CDP models, CDP parameter values, which are part of this calibration, right? Because you have an experimental study as a reference, you try to simulate that numerically. When you try to simulate the numerically, you try to take care of the failures, you try to take care of the overall behavior, and to obtain that, you need to play around with these parameters. So whenever you do any numerical modeling of any component, any structure, any analysis, first you should check whether the methodology of modeling, whether it's the type of element, whether it's the material property, boundary condition, all whatever you are going to consider should give you as close to the realistic behavior as possible. So if you have an experimental result of a certain specimen with all the input details, you should try to model that specimen first in your program, whatever you have chosen, and then try to get the closest result possible to the experimental one. Many a time it becomes difficult because the reference paper or the study which you are considering may not have all the input details, and then you have to assume. Once you are going to assume, it becomes some kind of hit and try. There is no option, but there is no other option. You have to do that. Okay, without validation, the your further studies, detailed studies using that methodology becomes questionable. Okay, anybody can ask, what is the basis that your methodology is correct? Okay, to justify that, validation is absolutely necessary. So for validation, these parameters get established. You have to play around with that. Right? So this was the simplified form for the material model and the tension and compression. So as you can see, this tensile strength, although this looks comparable with compression, this is just for the generic representation. We are not showing any values here. So the tensile strength for normal strength concrete, you can take approximately 1/10 of what you get in compression. That's what uh, past studies suggest and people consider. Okay, so cracking strength numerically is around 1/10 of the compressive strength related to the cube compressive strength. For cylinder compressive strength, again it changes. Right? Anyway, so this was the model for the steel reinforcing bar. So as you can see, whatever is considered the realistically, so it yielded around 415 MPa if 415 was considered, and you can see how much strength it can pick up, right? So it can pick up more than 20% to 22% strength, right? So depends on the strain level or so. Now, if you are looking at actual behavior of steel rebar, can it go up to here? In reality, rarest of the rare cases, still it will not go, because this much strain, 15% strain, 10% strain in a rebar, if you want to get even in wall, that needs lot of deformation, because that much strain in the rebar will require lot of bending. If you consider beam, if you consider column, if you consider wall, any kind of member, this much strain in rebar is practically impossible. Before that, the concrete is going to crush, definitely. Even if you have under reinforced failure, steel will yield, concrete will crack, steel will yield, but the strain will not reach this value. Before that, your concrete will be going away, right? But anyway, for numerical simulation completeness, you have to give the curve. So we provide this curve in any numerical model. So how was the analysis done? Again, depending on the requirement, you have two categories of analysis. When you are going to have the design level response, you do the linear elastic analysis, as I mentioned. When you are going to estimate the forces and moments of the stress resultant under actual condition, seismic evaluation, you have to do nonlinear static analysis, as I mentioned, which is pushover analysis. And then to simulate the dynamic behavior under actual condition, we go for dynamic analysis. There you need the damping to be modeled properly. So in the present study, dynamic analysis was not carried out, only the nonlinear static analysis was done. So primarily 6 models were used, because uh, the study was done for the first time with this multi-story wall with the slabs at different levels. So we thought that different cases have to be considered. So 2 different heights were considered. One was 10-story and there was 5-story. Now 10-story wall slab means more number of elements, more reinforcing bars, and when you are considering damage, the computational effort is more, right? So 10-story wall was considered with only concrete, just for the sake of study, and concrete damage plasticity was mentioned for the entire thing. However, no reinforcement was considered. Okay, when the 5-story wall was considered, less number of elements, we could do different permutations with reinforcement embedded, without reinforcement embedded, and so on. Okay, so these were the different cases. Okay, and then we have a shear wall standalone model without any slab, just to see how the comparison comes up. So these were the different models. So you had a building which was 10-story, you had a 5-story, and then this is only the wall with the slabs, and this is the only wall. Okay, so different nomenclatures were given. So these are the screenshots from the Abacus model. Okay. As you can see here, we had two walls along the length of the building, two walls along the width of the building. So depending on the direction of the analysis, the corresponding walls will play the major role. If you are doing the analysis by pushing the building along this direction, these two walls are going to contribute due to their in-plane action. If you are going to have the pushover along this direction, the width, these two walls are going to play the role. Right? These were the set of parameters, as you can see. Slab thickness was kept same. We did not want to vary the slab thickness, and the width of slab was also kept same wherever it was used. And then these are the thickness of the wall, height of the wall, and these were mentioned. Okay? And these were the reinforced. So for the different cases, as you can see, we took CDP for wall and slab only, and so on. So this was the reinforcement detailing at the slab wall junction. In order to transfer the forces and moments from the slab to the wall, you need to develop the rebars to the fullest extent as specified by the detailing guidelines. Okay, and then when we model the your slab, we can consider the small sized elements over the entire extent of the floor, right? Now, the more you make the element smaller in size, the number increases. And once the number increases and the damages start, your program becomes slower and slower when it is running. Okay. And many of the time it doesn't converge because nonlinear analysis involves a lot of iterations for which convergence is necessary. Right? So, in that respect, you may not be able to afford the small size of elements throughout your extent of the floor, right? So what was done, where we expect the damage, since the pushover was done in this direction, wherever we expected damage, in that vicinity, we provided elements with smaller size. In the far away regions where we do not expect that much damage in the slab, the coarse mesh was used. The mesh size was small. Okay. So here the mesh size was small, here the mesh size was large. So here you have the uh, mesh size. And also the rebars were also considered in this part, right? So because when you push in this direction, these two walls get active, wall A and wall B. So in this vicinity, we expect damage, as we had seen in that Chile earthquake figure, right? Fine. So let us look at the results quickly. So first, for any finite element study, we have to carry out the mesh sensitivity study. What is the size of the element you are going to use for your detailed analysis? You need to consider a few mesh sizes, see how the result varies, and then if you're not getting appreciable variation, you can use the larger size because larger size mesh is going to give you less computation time. Okay, you cannot spend hours and days and weeks for analysis. Okay, efficient way. So these were the damage patterns for the three cases. As you can see, there is very less difference in the damage extent. Even if you look at the end regions, if you look at the central region of the slab, the change in the damage patterns is very less. So this size of the mesh was adopted. Well, so this from here starts the interesting result. So this is your 10-story building, this is the 5-story building, and this is the standalone wall with only slab. Right? So what has happened here? If you look at the damages in this direction, it has been pushed. As you can see, it has moved in this direction, so it has been pushed in this direction. So you have very less damages in the columns. Hardly there is any damage. Here, the damages have spread across the height of the wall. So if you had modeled only this wall as a cantilever without slab, you would have observed all the damages here, just like a cantilever beam. At the end, you get the maximum moment, so you should expect maximum damage. But here, what has happened from top to bottom at different flow levels, right? The damages have happened, right? So the damage has been distributed across the entire height rather than concentrating at the base for the 10-storied as well and for the standalone case as well. Okay, so what does it mean? The damages are going to occur at the different floor levels, and story wise there is a repetition of the pattern, right? So instead of the entire wall behaving like a cantilever, if you see this story panel, the lower story panel, the bottom story panel, you can see a similarity of pattern getting repeated, right? If you look at the aspect ratio for this story, the height by length is almost giving like a squat configuration, right? If you consider the entire height of the wall divided by the length, it is definitely slender, highly slender. But these floors are kind of partitioning the wall into small story panels. So over each panel, you are encountering similar behavior, right? So within the story panel, due to the squat configuration, it is like that strut and tie action. It is like a shear behavior. So instead of this entire wall behaving like a vertical bending beam, cantilever beam, with the damage only at the bottom, instead of that, what the floors are doing, the slabs are doing, it is partitioning the walls into small, small panels, and each of them, it is distributing the damage. If you see, more damage is there at the junction, less damage in the body of that wall. Again, more damage at the junction, less damage in the wall. So that is getting repeated. Same thing here. At the junctions, you have more damages and the patterns are getting repeated, as you can see. Same thing here, right? So in the presence of slab, the walls are not behaving just like that vertical cantilever beams, what we expect, okay, for a standalone single wall case, isolated case. Rather, the damage is getting distributed and the slab is playing the important role, right? So you have that diagonal strut formation in each story. So whenever you have such kind of squat panel, whether it's squat wall, squat pier, and you apply lateral force, that strut and tie formation, just like the shear action, that happens. Okay, that is established structural behavior. So similar observation is being seen here. Okay, so this is the deviation. If you had a wall like this, you expect bending behavior here. Near the junction is the disturbed region. Here you expect shear behavior. But up to here, you expect like a vertical cantilever. But then when you look at the wall, we just extracted that part of the wall. At the slab levels, you are getting the damages. So the distinct difference in what you expect in the presence of floor slab rather than the isolated wall. Okay. So this was a major outcome, major finding for this one. Now let us look at the damage in the slab, tensile damage pattern in the slab. So as you can see, for the two cases, W1, WB2, depending on the parameters, here the spread of damage is less. In this case, the damage has spread more, right? So slabs are getting damaged. So what we observed in that 1985 Chile earthquake, that heavy damage at the slab wall junction, okay, that exactly is getting reflected here, right? So you have a portion of the slab getting damaged connected to the walls. So when you look at the plastic strain, there are different ways of quantifying damage in abacus. Okay, plastic strain in the equivalent form, that is one way. So depending on the uh, region of your wall, the plastic strains are larger, right? And then from the tension phase of the wall, you have more plastic strain here. Okay, so at first floor level, we have tried to figure out. Okay, so this is how you get it. So the strains in the rebars are also getting changed. That is what we get. Right? Then at the maximum drift level, you can see the comparison. This is for the cantilever wall, right? And this is for the wall with slabs. Same thing, compressive damage and the tensile damage. Okay, you can see the very clear difference. If you do not consider slab, how the behavior is changing. Okay, So again, for the equivalent plastic strain, it changes for the different cases, right? Then a parametric study was done that how we can do more detailed insight for this one. So for that, only the wall slab assembly was considered, not the entire building, because once we do parametric study, the building analysis will take more time, right? So that is how it comes up. So we had different models with varying amount of reinforcement. That was one parameter. Wall panel aspect ratio, the story height by the story length for the panel, then extension of floor slabs, okay, and the material properties was that. So different parameters were varied. So these were the summary of the different reinforcement details. Okay, what is the extension of slab? Let me show you here. So in this one, as you can see, the slab ends at the edge of the wall, right? Now here also it happens. What is happening here? We are extending the slab slightly beyond the edge of the wall. What is the intention? Because the damage can spread. So we need, or we want to allow the damage to spread as much as possible, because our intention is to see how much the slab is getting damaged. So that's why we extended the slab on either side of the wall by certain extent, right? So that is how this extension of the slab came into action. You can see very well the strut formation, whether the slab is extended or not. So it is getting repeated, and you can see these red zones. So at different levels, you have. So in these two, the steel percentage was less. Here, the steel percentage was more. In certain cases, you have the crushing of concrete at the junction, right? So um, very interesting behaviors came up. So when you play around with the these parameters, you can see the variation, right? The propagation of damage. Then at different levels of drift, 0.5% was very early when the damage just started. This is the moderate level damage, and this is the final drift. So what is the variation here? Here the panel aspect ratio was changed. So as you can see, this is a very squat panel. The story height by the length of the wall, that is less than 1. Here it is square, the story height by length of wall. Okay. Here the panel aspect ratio has made it slender. Height is more than the. So what is happening here? You can see the difference in the damages in the final drift level. You need not see the intermediate ones. So at the final drift level, as you can see, in all the cases, the slab is getting damaged. Now, how much the body of the wall is getting damaged depends on the aspect ratio. So here the panel is like a slender one. The body of the wall has got less damage. As you make it more squat, and so very importantly, the strut action is coming. Since it has been pushed like this is the compression flow path or the strut, right? As you can see, very vividly it is forming, okay, and the damages are happened, right? So this gives us very good insight that how the actual behavior can happen, right? So less damage propagation for this one in the body of the wall. Then different extents of tensile damage along the length of shear wall, these were plotted, okay. I'm not going into all the details because that will take time, okay. And these are the primary findings. So when you look at the tensile damage reaching the maximum value, these are the cases. So this is the damage level defined by the damage parameter. At the beginning of the CDP model, I had mentioned the damage parameter signifying the tensile damage and compressive damage, right? So this is how the maximum damage parameter is reached. How early they are reached and how uh, later on, how delayed way they are reached. So that defines the propagation of damage. If you have early propagation of damage at low drift level, the damage parameter reaches the value 1 very sharply. When the damage propagates slowly, then it reaches the maximum damage in a delayed way, right? So these are the ways to interpret the results, right? So the final outcome is that in our seismic design, this panel-wise behavior, so the flow levels. They are cutting across the entire wall into different panels. So panel-wise behavior is never considered and the associated failure modes. So probably the time has come to consider that. This is again the difference in tensile damage level for the higher reinforcement and less reinforcement. If you have less reinforcement, you expect damages to start early. That's what is reflected from this sharp rise and reaching the tensile damage of maximum value. For the 3%, it reaches less, right? It reaches slowly. So, increasing the minimum percentage of steel in the shear wall may probably lead to lesser damage in the floor slab because the propagation of damage is less, is slower. Fine. So to summarize, you have the formation of diagonal strut in the wall panel between the floor slabs. As we can see, the cracks on the tension phase, the crushing in the compression phase, they have all formed. Then you have damage at the lower drift level, depends on the aspect ratio, higher aspect ratio of wall panel and lower vertical reinforcement ratio. And then all these, whatever I have shown you, all these are part of the possibly beginning of a new seismic design methodology for floor slab. So we need to study more, we need to do more experiments in order to find out really how the slab is playing the role. We have observed certain damages, we through the actual failure of the building and that junction as well as the numerical one. But if we unless we do more experiments, we won't get that much practical insight. Okay, so a lot of possibilities are there in this way. So before I stop, again I acknowledge the Assam Royal Global University for giving me the opportunity to give the presentation and share with you whatever things we have learned. And then the Atal AICT scheme of Government of India, we are indebted to them also. Of course, all these work, what I have shown you, none has been done with my active participation. It was all done by Dr. Snehal Kaushik, who is happening to be one of the participants here also. So thanks to her extensive work, I personally have learned a lot of things. Department of Civil Engineering, where work since last 16 years. Many of the figures, as you have seen, has the reference of EERI. This stands for Earthquake Engineering Research Institute, right? If you have not visited that EERI, you can just have a look. There are many resources and there. So the many photographs of different failures, not only for these walls and so many things are there. It's a good repository also. And finally, her entire work was funded as stipend from this Ministry of Human Resource Development, Government of India. So we are indebted to them as well. Okay. Thank you for patient listening and any question on this part.
All right, thank you, sir. So if you permit, then I will ask the participants to ask their questions if they have any.
Yes, surely.
Yeah,
Sure.
I would request the participants to unmute themselves to ask questions if they have any, or put it up in the chat box. I can read that out. We'll wait a bit, sir, for
Yes,
the
sure.
participants
No
to
problem. No problem.
react. We are receiving appreciations from the participants for
Yes.
this insightful session. As you can see it, I think so.
Yeah.
Yeah, I have a query.
Yes. Manisha.
Sir, so in E-type modeling, generally if we do not provide the boundary element, then how can we model this shear wall? Suppose, so that is one question. I have another question also.
So in ETABS model, you are
ETAB or SAF.
SAF 2000.
Hmm.
Yes. So you want to model the wall without the boundary element.
Yes, yes.
So what will happen is, let me show you. Wait. Yes. So here, as you can see, like for this one, we did not have separate columns. Okay. So here the separate columns are not there. However, the wall itself is rectangular shape. The ends of the walls are always provided with more reinforcement. So these are like your boundary elements. So now this, if you want to model in ETABS, suppose you want to model like this, right? So what will happen? Instead of these end columns, you will have an entirely rectangular section, right? So you assign this equivalent frame element at the central location of the wall, assign rectangular section, okay, because you don't have these end columns. So it will be an entirely rectangular section for this entire height. The cross section will be rectangular. And then you connect with these beams. That is not a problem, because here what will happen? You will have this normal beam connected with this rigid link, again the rigid link connected with the normal beam on this side. So any shape of the wall, whether you have the end columns or whether you do not have the end columns, even if it is rectangular, so accordingly the property needs to be assigned to this equivalent frame element, and then the rest remains same. You connect the beams with these rigid links at different levels. Does it
Thank
answer?
you, sir. Yes,
Ah,
yes. Thank you, sir. I have
okay.
another query.
Yeah.
Sir, the PM interaction curve, is
Yes.
it same as, I mean, column?
PM interaction curve for wall is slightly different. Like if you look at the annexure of IS 13920 2016, which provides the design functions for this earthquake resistant shear wall or special walls, right? So in the annexure, there is a closed form expression for the bending moment for a rectangular wall section. One for the under reinforced case, there is one expression. Another expression is there for the over reinforced case. Okay. So there also you have, similar to the column that P by FCK BD, there also you have a parameter which is lambda. And then moment also you express in terms of M by FCK BD square in that form. Okay. So instead of using those curves, IS 13920 does not prescribe those curves. Rather than that, for any rectangular slender wall section, that is only for slender wall, those equations are valid. So for any slender wall section, depending on the reinforcement percentage, material properties, uh, the equations are prescribed. So in that way, if you do, the interaction will be slightly different. So you change lambda, you change P, you get different M. So you change P, you get M. And then if you plot, you will get an interaction curve, but it will be slightly different. Okay. So in SP16, what happens? You have two cases of rectangular columns for reinforcement distribution. One equally distributed on all four sides, and the other equally distributed on two sides, right? Actually, when you have shear wall and you have vertical bars in two layers, none of the cases is conforming to this shear wall case. Okay. In shear wall, you don't have this one, because in shear wall, along the length, you have the distribution of the bars. So neither it is rebars distributed equally on four sides of a wall, nor it is distributed equally opposite on two sides. Okay. So that's why the interaction curves given in SP16 for the rectangular column, they cannot be used directly. Even if you try to put the dimensions and so on, they cannot be used directly. But the basic principle is same. How you get the PM interaction curve for column as well as walls, that remains same, but the form of expression is different. The basic principle is same. It has to be.
But sir, in software like ETEP, we used to get the similar kind of PM interaction curve like the column. So
See, the profile will be similar, okay, but
okay.
then the values will be different. What I'm saying, you cannot use the SP16 values with B and D like that of wall. That will give you different values than what you'll get using the annex equations of IS 13920. See, the PM interaction behavior will be like that only. You'll have the maximum M close to the balance point. Okay, so you get the behavior similar to that. Okay. But then the values will be different. You cannot use the SP16 curves directly for walls. That's what I'm saying. Yes.
Okay, thank you, sir.
So I have one question here. Jagadish Bommisetti. Is there any database available for CDP parameters for different types of concrete? See, CDP parameters will change not only for different types of concrete, but for different components. Like if you do an analysis for the beam, right? Separate standalone beam model and do under vertical load, lateral load, whatever, the set of CDP parameters will change if when you try to match your abacus simulation results with that of experiment. Okay, for the same beam, if you change the grade of concrete and do the experiment, again the CDP parameters will change, right? So again, if you take for a column and change the grade of concrete, you get different sets of CDP parameters. So CDP parameters are going to be vary or going to be established for different components, different grades of concrete, even different rebar quantities also, right? Because the concrete is also related to your rebar influence, right? The steel reinforcing bar influence. So it is difficult to get a database. But then for different types of concrete, I'm not sure. If you want to get for particular beam, you can look for and get the database. If you want to see the results for column, you may get certain database. But that database also may not be extensively for all grades of concrete, all kinds of parameters, and so on, right? So those will be difficult. For I think walls with having low aspect ratio, squat walls, I think there was a study by Whitaker and some other people. So if you see look for walls of low aspect ratio, probably they have a document where different experimental studies were compiled and their CDP parameters have been mentioned. Okay, but as such, separate database for different types of concrete, I don't think it is available. Yeah. Okay, we have another question for design shear wall in ETABS. The shear wall will be assigned as membrane or shell. I think it has to be assigned as shell element because the difference between membrane and shell element will be like membrane will be having only the in plane forces, right? It cannot sustain moment, isn't it? Membranes cannot sustain moments. But then in shear wall, you need to have the in plane moment. Otherwise, you cannot design, right? So in shear wall, you will have the axial compression or axial force. You need to have the shear force. You need to have the moment. So you have to go for shell element. You cannot go for the membrane element. Right? Okay.
If we have more questions, we can take one or two.
Thank you, sir, for your insightful session. It was very informative.
Okay. I think
So
there's no more question as of now. Yeah.
Yeah. So
we can
if
have a
there,
group.
Sir,
yeah, we can have a group photograph.
Yes.
Or maybe we have a question there.
hello, sir.
Yes. Tell me.
Sir, for this share wall, we'll be following this IS code 13920, na? Right?
For
For designing.
earthquake resistant shear walls, yes, to follow IS 13920, that 2016 is the latest revision. Yes.
Okay, sir. Okay, sir. Thank you, sir.
Yeah. Thank you.
Well, we can go ahead with the photograph then for the attendance record. Rishikesh, you'd look into it.
Yeah, Jay is back. I think he'll take this picture.
Okay.
I'll
Okay,
tell
Jay is
this.
back.
Yeah.
Jay, are you back?
Yes. I'm here.
ठीक है, ठीक है, ठीक.
Okay, screenshot has been taken. Thank you so much, everyone.
Thank you so much, Jay, and thank you so much, sir, for this insightful sessions, like for the 2 sessions that you have delivered. And with this, we conclude day 3 of the FDP. Dear participants, thank you to you all as well. And on behalf of the organizing team, I extend a heartfelt thanks to everyone who has actively engaged in the sessions today. We look forward to meeting you tomorrow. Thank you so much. Good night.
Thank you. Thank you. Good night.
Good night.